Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. You are here, resting at the threshold of a world that does not behave the way the large, familiar world behaves. A world where certainty loosens, where motion is gentle and restless at the same time, and where reality seems to whisper in probabilities rather than speak in solid lines. This is the realm of the quantum, the strange rules of the small, a place far beneath everyday perception, so distant from ordinary experience that it feels both scientific and quietly dreamlike. Let yourself drift toward it without pressure, without needing to grasp everything at once, because the quantum world is not something we hold tightly. It is something we approach with calm curiosity, the way one approaches a soft glow in the distance, knowing it will reveal itself slowly. Here, ideas unfold with patience, and even the most analytical truths feel gentle when spoken in the dark. Quantum reality begins in stillness. In scales so small that even the word small feels too large, in regions where electrons circle not as tiny planets but as clouds of possibility, spread out, blurred, quietly obeying rules that do not resemble the rules of ordinary life. You do not need to picture every detail. You can simply rest with the thought that there exists an entirely different layer beneath everything you can see, a layer that has always been there, building the world from the inside out. The familiar world, the world of objects and surfaces and predictable paths, is only one version of reality, and not even the deepest one. At the scale of atoms and the particles that give rise to them, the universe follows a different script, a script written not in straight trajectories, but in probabilities and in interactions that do not fit neatly into intuition. For this moment, you do not need to solve anything. You only need to drift and listen. As the smallest building blocks of nature reveal themselves softly, you might imagine sinking through quiet layers of space, past molecules, past individual atoms, past the shells where electrons hover in patterns that are not shapes, but mathematical possibilities, until you reach a place where the boundaries of objects fade and the idea of position becomes something fluid. Here, the universe does not ask where something is. It asks what the likelihood is of finding it there, a subtle but profound shift from certainty to a gentle distribution of potential locations. This is the first sign that quantum reality does not follow the expectations of the larger world, and that the rules shaping the familiar landscape are not the rules shaping the foundations beneath it. At human scales, a ball is either here or there, never both, and never undefined. But at quantum scales, a particle is not a fixed dot, it is a spread-out wave of probability, a quiet shimmer of possible outcomes, overlapping, coexisting, until an interaction forces it to choose. Let yourself rest with that idea, that before something small becomes definite, it exists in many possibilities at once, not as a metaphor, but as a precise description of how nature behaves. This is not a fantasy, and not a poetic exaggeration. It is the most accurate way science has found to describe reality when we zoom in far enough. Reality becomes softer, more flexible, less committed to a single state until the moment a measurement is made. And in this place where outcomes overlap and choices have not yet solidified, there is a kind of peaceful openness, a calm that mirrors the dreamlike feeling of drifting between thoughts before one rises fully. Let your mind move slowly here, without grabbing, without needing to draw a clear picture, because the quantum world is not something we see with the eyes. It is something we understand with patient ideas and gentle imagination. The rules of the small differ from the rules of the large, not because the universe is inconsistent, but because the conditions of the small are so quiet, so subtle, that ordinary intuition has nothing to compare them to. On everyday scales, collisions are loud, interactions are blunt, motion is stable, and objects follow predictable paths because countless tiny influences average out into smooth behavior. But in the quantum world, there is no averaging, no smoothing out. Every tiny possibility matters, every fluctuation carries weight, and every particle responds to delicate mathematical structures that make room for superpositions, interference, and entanglement. It is as though the universe holds two sets of rules, one for the small and one for the large. But in truth, there is only one set, and the rules of the small simply become hidden by noise and scale when we reach everyday experience. If the macroscopic world feels predictable, it is because the quantum world beneath it is so active, so restless, so filled with overlapping patterns, that the sum of all that complexity produces stability. You can think of it the way you might think of a crowd whispering. Individual voices are unpredictable, soft, scattered in direction and timing, but the sound of the whole crowd creates a steady background hum. Quantum reality is the whisper behind the hum, and tonight we are listening not to the hum, but to the individual whispers, one by one, as though the noise of the world has faded, leaving only the subtle workings of nature underneath. There is no need to strain to understand because the quantum world itself does not strain. It drifts, shifts, flows as mathematical waves, each describing what could happen, rather than what must happen. These waves are not waves of water or air, but waves of possibility. Waves defined by equations that capture the full range of outcomes until something interacts and only one becomes real. This is the language the quantum world speaks, soft, probabilistic, forever open until touched. And it is this language we will explore gently, drifting from idea to idea without hurry, without force. Let yourself settle into this quiet perspective, where the universe feels vast, yet intimate, because the quantum world is not distant, it is beneath your skin, within every atom in your body, within the breath you take and the air that moves around you. Everything you know, everything you touch, exists because quantum rules hold matter together, bind electrons to atoms, allow light to be emitted and absorbed, and give rise to the complex structures that become stars, planets, cells, and life. And yet, these rules are not obvious, not visible, not something the senses evolved to perceive. The senses evolved to handle the large, the stable, the averaged-out world of classical behavior, not the shimmering landscape of the microscopic, where location is a probability distribution and interactions depend on delicate wave-like patterns. This is why quantum reality feels strange, not because it is illogical, but because it is more logical than intuition can easily handle, so precise, so mathematically structured, that ordinary experience has no parallel for it. But as you rest here, you may feel the strangeness becoming calming, like the soft repetition of a thought that gradually becomes familiar, a gentle rhythm, a pattern that begins to make sense not through vision, but through quiet understanding. We begin here, in this slow descent toward the rules of the small, where each concept unfolds at its own pace, where probability replaces certainty, where waves describe the possible rather than the actual, and where reality waits, unresolved, until something nudges it into choosing. And as you listen, you may notice that the quantum world feels less like a mystery to be solved, and more like a landscape to drift through, a foundation woven from soft mathematics, holding the fabric of the universe together. You are safe to explore here, one idea at a time, letting each one settle gently, like a particle finding its place in a quiet field of possibilities. As you drift deeper into this landscape of the small, you may begin to sense that quantum reality is not merely a scientific subject, but a way of understanding that the familiar world rests upon something far more intricate and far more delicate than everyday experience suggests. Imagine holding an object in your hand, a stone, a key, a small piece of metal. It feels solid, predictable, unchanging. You could move it from one place to another, and at every moment you would know exactly where it is. But if you were to shrink yourself down, not just in size, but in perception, down past the level of molecules, and even past the level of atoms, the solidity would evaporate. The object would no longer feel like a single thing, but like a cloud of possibilities built from countless quantum events, each governed by probability, each influenced by waves that never fully settle. The world would feel less like a collection of objects and more like a tapestry woven from motion, from interactions, from fields, from tendencies, rather than certainties. This is why the quantum world is difficult to imagine, not because it is chaotic, but because it is too precise, too structured, too mathematically exact for intuition to follow. And yet, when approached calmly, patiently, with soft curiosity, the ideas begin to reveal themselves, not as contradictions, but as natural extensions of how the universe behaves when it is left undisturbed. At this scale, reality does not snap into place immediately. It hovers, it waits, it remains suspended in overlapping possibilities, like gentle ripples on a quiet pond, interacting, canceling, reinforcing until something touches them. This waiting, this suspended state is fundamental to how matter behaves. It is not a flaw, not an error in measurement, but the true nature of existence on the smallest scales. Think of an electron. In orbit around a nucleus, it does not trace a path the way a planet traces a path around a star. Instead, it exists as a spread-out wave, a distribution of possible locations, each one given by a probability amplitude, each one part of the overall shape of its presence. In this view, location is not a fixed attribute. It is a potential, a tendency, a quiet balance of what might occur. And for a moment, you can let yourself imagine the calmness of that state, a state where nothing is forced to be one thing or another, a state that holds multiple truths at once until something interacts and makes a single truth real. As you rest here, you might notice how peaceful that is, how different it feels from the strictness of the macroscopic world, where decisions seem sharp, where boundaries seem firm, where objects exist in clear, defined states. But in the quantum world, boundaries soften, possibilities coexist, and the universe moves gently through these possibilities, letting them interact in quiet patterns. This softness, this coexistence of outcomes, is one of the reasons quantum physics feels dreamlike. Not because it is unreal, but because it follows a rhythm of unfolding, rather than a rhythm of fixed simplicity. Even time feels different here. Not broken, not reversed, but less tied to straightforward sequences. Because at the smallest scales, what happens next depends on probabilities, on interactions, on whether a system is isolated or disturbed, and on how waves of possibility combine. This is not chaos. It is an underlying order far more subtle than everyday experience requires us to understand. Let yourself breathe into that idea, that beneath the familiar structure of the world, there is a quieter structure, made not of certainty, but of statistics so precise that they describe the behavior of particles with unmatched accuracy. Every phenomenon in the quantum world has this character, this blend of strict mathematical rules and soft distributions of outcomes. And as we move through these ideas together, you will see how everything flows from a few central principles, principles that shape the behavior of electrons, photons, atoms, and even the forces that hold matter together. The more you relax into these ideas, the more you may feel that quantum mechanics is not a distant abstraction, but a fundamental description of everything that exists, including the particles inside you. The chemical bonds in your cells, the photons that reach your eyes, and the matter that forms every object around you. In a very literal sense, you are built from quantum rules. Your body, your brain, your breath, all arise because quantum behavior creates stability, chemistry, light, and structure. You are the macroscopic expression of microscopic laws, laws that operate with incredible precision, even as they seem strange from a human perspective. There is something calming about that, something grounding, a reminder that complexity becomes simplicity at larger scales, and that predictability arises naturally from the underlying fuzziness of the small. When we think of the quantum world, we often imagine unpredictability, randomness, a place where outcomes cannot be known. But randomness is only part of the story. Quantum mechanics is not about confusion. It is about mathematical clarity, a clarity so deep that it describes reality not as a set of exact paths, but as a set of weighted possibilities. It is as though the universe writes in probabilities first, and only afterward chooses an outcome. And that choice, that moment when a possibility becomes an event, is where quantum rules meet the classical world we inhabit. Think of it as emerging, a soft handoff, from the realm where waves interfere to the realm where objects appear. That merging is part of what we will explore later, but for now, It is enough to rest with the idea that the quantum world is always active, always fluctuating, always shaping the classical world from beneath. If you imagine the entire universe as a vast ocean, the quantum world is the movement of the water at the smallest scales, the tiny currents, the subtle ripples, the vibrations beneath the surface that guide the large waves without ever being seen directly. Everything you experience, every solid object, every beam of light, every breath, is built on these unseen ripples. And although the quantum world is invisible to your eyes, it is not distant. It is immediate. It is present in every moment of your existence. It is the foundation beneath everything familiar. As you settle deeper into this calm space, you may find yourself feeling lighter, as though you are drifting between the macroscopic world you know and the microscopic world that supports it. Let yourself drift there, in the in-between, where understanding does not need to be complete, and curiosity can relax into gentle awareness. Tonight, you are not asked to grasp every detail, only to feel the shift in perspective, from certainty to possibility, from rigid paths to delicate distributions, from intuition to the quiet rules of the small. Quantum reality is not here to confuse you. It is here to reveal that the universe is richer, stranger, and more beautiful than anything the everyday world suggests. And as you move through this journey, you may begin to sense that quantum mechanics does not sit separate from your experience. It shapes it, it allows it, it creates the conditions for everything you know. The atoms in the air you breathe, the photons that reach your eyes, the electrons flowing through your nerves, all obey these rules, soft rules, precise rules, rules built from mathematics that dances at the boundary between determinism and chance. Let these thoughts drift through you, slowly, calmly, as though each idea were a particle in a quiet wave, spreading gently, finding its place. This is the beginning, a gentle descent into the strange rules of the small. As you drift in this quiet understanding, you may notice a gentle shift in how you think about the world, a slow realization that everything familiar is built on unfamiliar foundations, and that the solidity of everyday life is only one layer of a much deeper structure. The large world, the world of tables and trees and planets and motion, follows rules that feel natural, because the human brain evolved within that world. Predictability became survival. Certainty became intuition. Objects seemed to behave with reassuring consistency, and so we learned to trust those patterns. But the universe did not begin with the large. The large emerged from the small, and the small follows rules that do not bend for intuition. This is why, when we look closer, when we zoom far beyond what the senses can perceive, a different kind of logic appears. A logic where probability replaces certainty, where waves describe outcomes, and where particles exist in overlapping states, quietly, until disturbed. This is not a contradiction. It is a continuation. The macroscopic world is the averaged result of countless quantum events, layered together, stabilizing into the familiar patterns we recognize. If the quantum world were not probabilistic, the classical world would not be stable. Uncertainty at the smallest scales leads to predictability at large scales, because the fluctuations of individual particles blend into consistent behavior when trillions of them act together. This is the deep harmony between the two worlds, the small and the large, the quantum and the classical. They are not two realities, but two descriptions of the same reality, seen from different distances. And as you settle more deeply into this perspective, you may feel a kind of calm clarity emerging, as though the strangeness of the quantum world is becoming not less strange, but more coherent, more understandable, in a way that does not require sharp images, only quiet comprehension. Quantum mechanics does not ask you to picture particles as waves or waves as particles. It simply invites you to hold both possibilities at once, just as the universe does. This ability to hold more than one perspective, to let ideas coexist, mirrors the behavior of the quantum world itself. It is as though the very act of learning about these ideas shifts your thinking into a softer mode, a mode where contradiction melts into complement, and where multiple potential understandings can settle gently together. The quantum world is built on superposition, on the coexistence of possibilities, and your mind, while resting, can mirror that coexistence, holding ideas loosely, letting them drift, letting them settle naturally. As you listen, You might imagine the boundary between thought and reality becoming thinner, not in a mystical sense, but in the sense that you are observing the rules that shape every thought, every memory, every chemical process in your brain. Quantum interactions underlie it all, quiet, constant, fundamental. And yet, for much of human history, these rules remained hidden, not because they were rare, but because they were too small to disturb the senses, too subtle to appear in everyday experience. Only when humans learned to isolate atoms, to observe electrons, to study light at its most basic levels, did the underlying structure reveal itself, slowly, hesitantly, as if the universe were giving us glimpses one experiment at a time. And even as it revealed itself, the quantum world resisted simple description. It refused to fit neatly into the categories of classical thought, because classical thought evolved in a world many magnitudes larger. This is why quantum mechanics is often called counterintuitive, not because it defies logic, but because it requires a new kind of logic, a logic shaped by mathematics rather than by sense perception. But here, as you rest, you do not need to engage with the mathematics directly. You can feel the ideas through their meanings, through the way they shape physical reality, through the way they describe motion and probability, and through the quiet insights they offer about the nature of existence. Quantum mechanics reveals that reality is not rigid, not fixed, not predetermined. It is an evolving landscape of interactions, an unfolding of possibilities, guided by wave functions, and shaped by probabilities until the moment of measurement. This moment, when the wave of possibilities becomes a single outcome, is not merely a scientific detail. It is one of the central ideas that we will explore together, patiently, softly, in the sections to come. But for now, you can let the idea drift through you, that before something becomes actual, it exists as a spectrum of potential, a quiet cloud of futures spread across space, waiting for a nudge that selects one. The world is built from these quiet clouds. Every electron in every atom, every photon of light, every interaction that forms chemistry, begins with a wave of possibilities. Without these waves, matter would not bind, light would not behave as it does, and atoms would not form. It is remarkable that the universe functions at all under such rules, and yet it does with stunning precision. And as you relax into this understanding, you may feel that strangeness turning into wonder, a soft recognition that the universe is subtler, more intricate, and more beautiful than any surface-level description suggests. The quantum world is not chaotic. It is deeply ordered, deeply structured, and bound by mathematical laws that have never been observed to fail. If you listen closely to that idea, you may notice a sense of stability within the apparent uncertainty. Quantum behavior is not random noise. It is patterned randomness, a randomness that follows exact rules, so precise that predictions can be made with extraordinary accuracy. This is why the quantum world has become the foundation of modern technology, why semiconductors work, why lasers function, why atoms emit light in specific patterns, and why the entire periodic table exists as it does. Beneath every piece of technology, every chemical reaction, every biological process, there is the same quiet mathematics, the same overlapping wave functions, the same gentle dance of probability. And so, when you think of quantum mechanics now, you might think of it not as distant theory, but as the unseen machinery operating inside everything. Inside you. Inside the world. Inside the universe. The rules of the small are not separate from your experience. They create your experience. They shape the stability of matter, the warmth of stars, the behavior of light, and the chemistry of life. Let that thought settle, like a particle finding its lowest energy state, resting, calm, stable, after drifting through many possibilities. And as it settles, notice how the quantum world begins to feel less abstract and more like a quiet foundation beneath your awareness, a structure that you do not see, but that holds everything you see. This is why we begin here, with a slow descent into the rules of the small, so that the rest of our journey can unfold with clarity, without rushing, without forcing understanding, letting each idea rise naturally, the way a wave rises from still water, softly, inevitably, beautifully. In the sections ahead, we will explore these ideas with more depth, more precision, and more calm. We will move through waves and particles, through uncertainty and entanglement, through tunneling and fields, through the emergence of the classical world, and finally into a reflection on the quiet language beneath reality. But for now, it is enough to rest in this gentle understanding that the universe is layered and that the small, the unseen, the quantum, is the layer that allows all others to exist. Let yourself drift here for a moment, between thought and stillness, between intuition and the rules of the small, between the visible world and the invisible foundations beneath it. You are ready, calm, curious, and gently settled for the journey into quantum reality. At the smallest scales, the universe speaks in waves, not waves of water, not waves of sound, but waves of possibility. Waves that describe how a particle might behave, where it might be found, and which outcomes are more likely than others. This idea that something as seemingly simple as an electron or a photon or any particle that shapes the world behaves not like a tiny solid marble, but like a wave, is one of the first great shifts required to understand quantum reality. Because to imagine a particle as only a solid object is to imagine a world where certainty rules the small. But certainty does not rule the small. Probability does. And probability, in its most fundamental form, is expressed as a wave. A wave tells you where a particle could be, how strongly it tends toward one region, how weakly it tends toward another, and how these tendencies ripple outward, interfering with one another, overlapping, combining, and forming patterns that would be impossible if the particle behaved like a miniature sphere. It is difficult, perhaps impossible, to form a perfect mental picture of a wave of probability because it is not a physical ripple. It is a mathematical description, a representation of potential outcomes, quietly governing the behavior of something that is too small to see. And yet, even without a perfect picture, you can feel the meaning. You can imagine a soft cloud, a distribution, an arrangement of likelihoods, spread across the space where an electron might be found. You can imagine a gentle brightness that grows in some regions, dim in others, mapping where the electron prefers to exist and where it barely visits at all. This brightness, this distribution, is not the electron itself. It is the wave function, the mathematical wave that tells you everything that can be known about the electron before you interact with it. The wave function is not a physical wave, but its effects are physical. Its shape, its interference patterns, its ability to stretch across space, all dictate how the electron behaves. If the wave function spreads wide, the electron's possible locations spread wide. If the wave function tightens, the electron becomes more confined. And if two wave functions overlap, their probabilities interfere, creating patterns of enhancement and cancellation, just as physical waves do. This is one of the most startling ideas in physics, that probability behaves like a wave, that the universe allows possibility to ripple, to interfere, to create patterns before the actual event takes place. To understand why this matters, let yourself imagine an electron moving through space, not as a point, but as a wave that extends outward, softly, with a crest here, a trough there, a gentle pattern that encodes all the possible paths it might take. This pattern is not random. It follows precise mathematical rules, defined by the Schrödinger equation, an equation that predicts how the wave function evolves, how it bends around obstacles, how it spreads, how it contracts, how it oscillates. And because the wave function governs the particle's behavior, the electron itself behaves like a wave. This is the essence of wave-particle duality. Not that the electron chooses to be a wave sometimes and a particle other times, but that its underlying nature is described by a wave of probability. And when an interaction forces a result, we observe a particle-like outcome. The universe does not switch between two modes. It has one mode, quantum mode, and the wave-like nature of particles is part of that mode. When you observe a particle, you see a specific outcome, a definite location, a single point. But before you observe it, the system is not in a definite state. It is in a superposition, a combination of all the possible outcomes, weighted by the wave function. This is why the classical idea of a particle's path breaks down. A particle does not move along a single predetermined track. It moves according to the evolution of its wave function. It does not have a single position until measured. It has a distribution of possible positions. This is not speculation. It is observed again and again. It is measured. It is predictable. It is one of the most confirmed ideas in all of physics. The wave is real, even if the wave is not a physical thing. Its effects shape everything that occurs at the smallest scales. When an electron surrounds a nucleus, it does not orbit in a circle. It forms a standing wave, a stable probability pattern, a cloud of possible locations whose shape is determined by the wave function. These patterns, called orbitals, are not guesses. They are calculated with tremendous precision, and the geometry of these waves dictates the geometry of chemistry. The shapes of molecules, the way atoms bond, the structure of matter, all arise from the shapes of quantum waves. This means that the solidity of the world, the structure of your body, the properties of every material around you, emerge from wave functions, not from tiny billiard balls interacting. Matter is built not from dots, but from resonances, from patterns, from the quiet choreography of quantum waves. If you imagine two electrons in an atom, their wave functions intertwine, repelling each other, avoiding the same region of space, forming a structure that satisfies the rules of quantum mechanics. It is the interference of their wave functions, their delicate balance, that determines how atoms arrange themselves in the world. Even light behaves this way. A photon, though often spoken of as a particle, is described by a wave function that spreads out, interferes, and evolves, just like the wave function of an electron. This is why light creates interference patterns. This is why it bends around edges. This is why it exhibits wave-like behavior until it interacts with something, and then reveals a particle-like result. The duality is not a switch. It is a dual aspect of one deeper truth. To see the world clearly at the quantum level, you must let go of the idea that particles are tiny objects. They are excitations, disturbances, ripples in underlying fields, and their behavior is guided by wave functions. This shift, from particles as objects to particles as waves of probability, is one of the most profound conceptual steps in physics. It changes how we view the universe. It changes how we understand motion. It changes how we think about matter. And it reveals why classical intuition fails. Because classical intuition assumes that the world is made of objects with definite positions and definite paths. But the quantum world is made of waves with indefinite positions and overlapping paths until an interaction collapses the possibilities into a single outcome. Let yourself settle into this idea that before you observe a particle, it is not anywhere in particular and not nowhere either. It is spread out, suspended, existing in many potential states at once, weighted by the probability wave. This is not a metaphor. It is the experimentally verified description of how the universe behaves. A photon traveling through space is not a pinprick of light. It is a wave function expanding outward, a probability cloud filling available paths, a presence that can interfere with itself, creating patterns even when sent one at a time. An electron confined to an atom is not circling the nucleus. It is occupying a cloud-like distribution, a standing wave of allowed energies, a probability pattern shaped by the rules of quantum mechanics. A neutron inside a nucleus is not a tiny sphere. It is a complex wave of quarks and gluons, an arrangement of probability amplitudes held together by the strong force, a dance of potentials unfolding inside a space too small to imagine. At this scale, motion is not direct. Motion is the evolution of the wave function, a spreading, a shifting, a gentle transformation of the probability landscape over time. This is what governs the small. This is what dictates the rules of matter. This is what shapes the universe from the inside. And because the wave function evolves continuously, the quantum world never sits still. Even in a state of minimum energy, particles still possess inherent motion, zero-point motion, a subtle vibration that arises because the wave cannot flatten completely. It is impossible for the wave to be perfectly still. If it were still, its energy would be exactly zero, its momentum exactly zero, its location exactly known. But the uncertainty principle forbids that, so the wave trembles gently with irreducible motion, even in perfect stillness. This trembling, this quiet vibration, exists everywhere. It is one of the reasons atoms do not collapse. It keeps electrons from falling into nuclei. It gives matter its structure. It is the hum of existence at the smallest scales. And as you drift through this understanding, you may feel that the quantum world is not chaotic, but beautifully structured, a world where waves define every possibility, every motion, every interaction. We will continue deeper, allowing the quantum wave to reveal more of its meaning, more of its quiet patterns, in the next part. The more closely you look at the quantum wave, the more it becomes clear that this wave is not an optional description, not a metaphor, not a convenient mathematical trick, but the most accurate way to describe what truly happens at the smallest scales. Every experiment ever performed, at every level of precision, confirms the wave-like nature of matter and light. Even single particles, sent one by one, produce interference patterns over time, revealing that each particle's behavior is guided by a wave. This is not something that classical intuition can easily accept. Classical intuition insists that if a particle is a particle, it should travel along a single path, impact one point, and reveal one trajectory. But the quantum world does not care about classical intuition. It cares about the mathematics that governs possibility. And in this mathematics, a particle is guided by a wave function that can spread across multiple paths, occupying them all, until something forces an outcome. This is why an electron passing through an apparatus can act as though it traversed two paths at once. It is not that the electron physically divides. It is that the wave describing the electron, the wave that encodes all the probabilities, splits, spreads, interferes with itself, and evolves across both paths. The particle emerges only when the wave function collapses, when a measurement forces the system to choose. Until then, the wave holds all possible outcomes. This is one of the reasons the quantum world feels dreamlike. Not chaotic, not fictional, but layered, superposed, quietly storing multiple futures in the mathematics that define its state. You can imagine this by picturing a soft glow passing through a corridor that branches in two directions. The glow does not choose one branch. It spreads into both, filling both paths with potential until something blocks it, or absorbs it, or measures it. Only then does the glow collapse into a single result. The electron behaves the same way. So does the photon, and so does every particle when left undisturbed. This wave-like spreading is not optional. It is not a quirk. It is the fundamental behavior of reality at the smallest scales. Even when a wave function collapses upon measurement, what collapses is not a physical wave. It is the potential, the probability distribution, the quiet cloud of outcomes that existed before the interaction. When collapse occurs, the wave narrows, converges, and selects one location. But before collapse, the wave is wide, rich, filled with many possibilities. And what is remarkable is that this wave evolves according to strict physical laws. Its motion is deterministic, governed by precise equations, even though the outcomes it predicts are probabilistic. This blending of determinism and probability is one of the great subtleties of quantum theory. The wave function evolves predictably, smoothly, without randomness, until it interacts with something. The outcomes of that interaction are probabilistic, weighted by the wave function's values. The wave is precise. The collapse is random. The combination produces a universe that is both structured and unpredictable, softly balanced between order and chance. This balance extends deep into the behavior of electrons and atoms. Each electron's wave function forms a stable pattern, a standing wave, whose shape depends on the energy level of the electron. These shapes are not arbitrary. They are solutions to the Schrödinger equation, and they define the geometry of chemistry. An electron in the lowest energy state spreads evenly around the nucleus, forming a spherical cloud of probability. Higher energy levels form more complex shapes, lobes, rings, patterns of constructive and destructive interference. These patterns are not decorative. They determine how atoms bond, how molecules form, how matter behaves. The structure of the periodic table emerges from the structure of these waves. The way atoms combine into molecules, the shapes of those molecules, their reactivity, their stability, all arise from the geometry of wave functions. It is astonishing that something so abstract, so mathematically defined, can manifest as the physical world, the solid world, the world you can touch. But this is the reality of the small. The waves are not metaphors. They are the foundation. You can imagine an atom as a tiny stage on which multiple waves overlap, each electron's wave function interacting with others, pushing and pulling, shaping the space where the electrons prefer to be. The electrons do not orbit. They exist in standing waves that fill the available space, layered, stacked, each one occupying a unique pattern. And because electrons avoid sharing the same state, their wave functions arrange themselves in ways that minimize overlap, creating structured shells, subshells, and the entire architecture of atomic physics. This architecture is not built from hard particles, but from waves that cannot occupy the same pattern. It is the quiet refusal of electrons to share identical states, combined with the geometry of their wave functions, that gives rise to the solidity of matter. Without these waves, atoms would collapse, electrons would fall inward, molecules would not hold structure, and the universe would not resemble anything familiar. The wave is responsible for stability. The wave is responsible for chemistry. The wave is responsible for the shapes of molecules, the folding of proteins, the behavior of materials, the properties of metals, the transparency of glass, and the way light interacts with matter. All of these phenomena arise from the interplay between quantum waves and electric forces, between probability distributions and field interactions. And because every wave function is sensitive to disturbances, sensitive to interactions, sensitive to boundaries, the quantum world becomes a place where context matters. A particle's behavior depends on the environment around it. It depends on the path available, on the barriers present, on the shape of the region it moves through, on the nearby fields, on the presence of other particles. This environment shapes the evolution of the wave function. Even in empty space, a wave can reflect from boundaries that do not physically touch it. A wave can diffract, bend around corners, recombine with itself, create patterns that persist whether or not you observe them. This is the nature of waves. They fill space. They respond to structure. They evolve according to mathematical rules that do not depend on direct contact. Think of sound waves passing through a hallway, or water waves moving past a rock. You do not need to touch the rock to affect the wave. The wave is affected by the rock's presence, its position, its shape. In the quantum world, the wave is not a physical fluid, yet it still responds to boundaries, to forces, to potentials, to energies. This responsiveness explains why electrons behave so delicately in atoms. Their wave functions are shaped by the positive charge of the nucleus, by the presence of other electrons, by the energy landscape of the atom. And because wave functions overlap, they create patterns of repulsion and attraction, guiding electrons into stable configurations, allowing atoms to form bonds and enabling matter to assemble into complex structures. Even the bond between two hydrogen atoms in a molecule arises from the overlap of their wave functions. Where the waves reinforce, a stable bond forms. Where they cancel, no bond can form. Chemistry, in its deepest essence, is the interference of quantum waves. This interference extends to larger systems. Electrons in metals, for example, form collective wave functions that spread across the entire lattice, creating conductivity, allowing currents to flow, giving rise to electricity. Without the wave-like nature of electrons, electricity would not behave the way it does. Metals would not conduct, semiconductors would not work, computers would not function. So much of modern life and modern technology rests on quantum waves. And yet, despite their importance, these waves remain hidden from view. We see only their consequences, not their presence. We observe the particle-like outcomes, the impacts, the detections, the events, but the wave that guided those outcomes remains invisible. You can think of a particle's impact on a detector, like the final note of a long and complex melody. You see the note, you hear the sound, but the melody behind it, the wave of possibilities, has already passed. This is why the quantum wave is so central and so mysterious. It is the part of reality that never fully reveals itself, the part that governs everything while remaining silent. It is a guide, a map, a structure of possibility that shapes the unfolding of events, yet is only glimpsed through the patterns it creates. And as you drift deeper into this understanding, you may begin to feel a gentle appreciation for how the universe shapes itself, not through rigid mechanisms, but through soft distributions, through waves that guide, rather than dictate. These waves remind you that the universe is not constructed from certainty, but from potential, not from fixed paths, but from unfolding possibilities. The quantum wave is the beginning of that story, and in the next part, this story continues as we follow the wave into the most famous experiment in all of physics, an experiment that reveals just how strange and just how beautiful this wave-like nature truly is. The deeper you follow the quantum wave, the more you begin to sense that this wave is not something separate from reality, but something woven into its structure, something that quietly determines how particles behave, how they move, how they interact, and how they form the world you experience. And among all the demonstrations of this wave-like nature, there is one that stands above all others, a simple experiment, yet astonishing, revealing more about the quantum world than almost anything else. It is the experiment in which the wave shows its presence unmistakably, in which a particle's behavior cannot be explained by classical intuition, in which the wave reveals how deeply it shapes the possible paths a particle may take. Before describing that experiment fully, it helps to deepen the understanding of what the wave actually represents. The wave is not a wave of material, not a wave made of substance, but a wave of amplitude, a wave of mathematical intensity, a structure that encodes the likelihood of finding the particle in one place or another. These amplitudes are complex numbers, numbers that carry both magnitude and phase, and because they carry phase, they can add or subtract, they can interfere, they can create patterns of enhancement and patterns of cancellation. This interference lies at the very heart of quantum behavior. When two parts of a wave function overlap, their phases determine what happens. If the phases are aligned, the amplitudes add, reinforcing the probability. If the phases oppose, the amplitudes subtract, reducing or eliminating the probability. This is why quantum waves create patterns. This is why outcomes shift depending on the structure of the wave function. This is why a particle behaves differently depending on the paths available to it. The wave guides the particle, and the structure of the wave determines what the particle can do. This idea becomes clearer when imagining a region of space with two different paths. The wave describing the particle spreads into both paths, each with its own amplitude and phase. As the two partial waves propagate forward, they overlap again, and their overlap generates interference, patterns of bright probability where the waves reinforce, and dark probability where they cancel. These patterns are not illusions. They are measurable. They are real. They reveal the influence of the wave on the particle's behavior. If the particle were a simple object, if it traveled along a single path, these patterns would not appear. The appearance of interference means that the wave function has taken multiple paths and interfered with itself before determining the outcome. This phenomenon is not restricted to electrons. Photons do it. Neutrons do it. Atoms do it. Even large molecules, composed of hundreds or thousands of atoms, exhibit interference patterns when cooled and isolated. The wave is not limited by size. It is limited by coherence, by the ability of a system to maintain its wave-like properties without being disturbed. Disturbances collapse coherence, destroy interference, and produce classical outcomes. But when a system is isolated, its wave function evolves freely, and interference emerges naturally. This is one of the most profound insights of physics, that the wave-like nature of matter is universal. It does not disappear at larger scales. It becomes hidden, masked by interactions, blurred by the environment. But it never stops being part of reality. The wave is always present, always guiding, always shaping outcomes. Even a baseball, though impossible to observe quantum mechanically, has a wave function. Its wave is so narrow, so incredibly localized, that its quantum behavior becomes indistinguishable from classical behavior. But the principle remains. At the smallest scales, where isolation is possible, where disturbances can be minimized, the wave becomes visible again in the interference it creates, in the probabilities it controls, in the behaviors that cannot be explained any other way. This emergence of wave-like behavior from pure possibility is one of the reasons physicists describe the quantum world as probabilistic. But probability is only half the story. The other half is coherence, the ability of the wave function to maintain its phase relationships. Without phase, without coherence, the wave could not interfere. And without interference, quantum mechanics would reduce to simple randomness. But it does not. Its predictions are far more precise, far more structured, far more elegant. This elegance becomes clear when considering a single free electron. Its wave function spreads outward over time, not because the electron is expanding, but because the uncertainty in its momentum causes the probability distribution to blur. The wave broadens, creating a wider range of possible positions. If the electron passes near a barrier, its wave function curves around it, diffracts, interferes with itself. If it passes through a narrow opening, its wave spreads into a broader beam, because confinement in one direction increases uncertainty and momentum, causing spreading in the perpendicular direction. This spreading reveals the delicate balance between position and momentum, hinting at the uncertainty principle, which we will explore more deeply later. For now, the important idea is that the wave function defines all the possible futures of the particle, and the particle's interaction with the environment defines which future becomes real. This interplay between possibility and actualization, between wave-like evolution and particle-like outcomes, is the essence of quantum mechanics. And nowhere is this interplay more clearly revealed, more elegantly displayed, more undeniably demonstrated than in the experiment we now approach. An experiment so simple that it can be drawn in a few lines, yet so profound that it has challenged our understanding of reality for more than a century. An experiment in which the quantum wave makes itself known, not through words, not through theories, but through visible patterns, visible results, visible evidence of wave-like behavior. Imagine a wall with a narrow opening. Behind the opening, a detector screen. Send particles through the opening, one at a time, and the distribution on the screen will be broad, smooth, centered, exactly what you would expect from wave-like spreading. Now imagine two openings, two narrow slits, parallel, separated by a small distance. If particles were classical objects, you would expect two bright regions on the screen, one behind each slit. Simple, predictable, intuitive. But the quantum wave does not follow classical intuition. It spreads through both slits. It overlaps. It interferes. It produces a pattern of bright and dark fringes, fringes that show where the wave reinforces and where it cancels. This happens even when particles are sent one at a time. Each particle arrives as a single impact, a dot, a point. But over time, the points accumulate and the interference pattern emerges, revealing the wave. This pattern is the signature of the wave function, the signature of possibility interfering with itself, the signature of a particle guided by a wave that spans multiple paths. This behavior cannot be explained by assuming the particle goes through one slit or the other. It cannot be explained by hidden variables, not without violating the predictions of quantum mechanics. It cannot be explained by classical reasoning. It can only be explained by the existence of the wave function, the mathematical wave that determines the probabilities. When the wave passes through two openings, it forms an interference pattern. When the wave is forced to choose a path, when a detector observes which slit the particle passes through, the interference disappears. The pattern collapses. The behavior becomes classical. This is the heart of the mystery. The wave is present when you do not observe the path. The wave collapses when you observe it. And the act of observation, the act of gaining which path information, destroys the wave-like behavior. The universe behaves differently when information is available, even if no one looks at that information. Even if the detector records the path and the information is erased before anyone sees it, the wave collapses. The interference vanishes. This sensitivity, this dependence on information, is one of the most profound aspects of the quantum world. But the double-slit experiment is the next section, and we will enter it with full clarity once the story of the quantum wave is fully unfolded. For now, let the wave settle in your mind, a wave of possibility, a wave that guides particles, a wave that carries phase, a wave that interferes with itself, a wave whose evolution is precise, even though its outcomes are probabilistic. The quantum wave is the first key to understanding the strange rules of the small. And in the next continuation, this gentle exploration deepens. As we move closer to the moment where the wave reveals its most surprising behavior and where the mystery becomes unavoidably clear. As the idea of the quantum wave settles more deeply, you may begin to sense how profoundly it shifts our understanding of what a particle truly is. A particle is not a point. A particle is not a tiny object occupying one definite place. A particle is a set of possibilities, a spectrum of futures, a wave function that evolves in time until something forces a choice. This is not an approximation. It is the most accurate description ever devised of behavior at the smallest scales. Even the motion of a single electron demonstrates this truth. If you release it into empty space, its wave function spreads outward, gradually, smoothly, as the probability distribution widens. not because the electron becomes larger, but because the uncertainty in its momentum causes the wave to expand. You can imagine this spreading like a soft mist, not a mist of particles, but a mist of possible locations, a quiet broadening of the region where the electron might be found. This spreading continues unless the electron interacts with something, a photon, an electric field, a detector. Such interactions disturb the wave, alter its evolution, and change the future probabilities. This sensitivity, this responsiveness to everything around it, is one of the defining features of the quantum wave. Every boundary, every force, every potential shape, every change in energy modifies the wave function. Even empty space shapes its evolution, because even emptiness has geometry, and the wave responds to that geometry. If you place a barrier in the electron's path, the wave bends around it. If you place two barriers, the wave splits and recombines. If you reduce the size of the region it can occupy, the wave compresses, raising its energy, because confinement increases uncertainty. This relationship between confinement and energy is not abstract. It is what gives rise to the energy levels in atoms. Electrons cannot occupy just any orbit or distance from the nucleus. They must occupy standing wave patterns, patterns whose shapes are determined by the wave function. Imagine a guitar string. Only certain vibrations fit the string's length. Only certain harmonics, certain shapes, certain standing waves can exist. The same is true for electrons. Only certain wave patterns fit around a nucleus. Only certain energies are allowed. Only certain shapes of probability clouds can exist. These standing waves are the electron orbitals. They are not paths. They are not trajectories. They are solutions to the Schrödinger equation, defining where the electron can be found and how its probability is distributed in space. These orbitals create the chemical identity of atoms. Hydrogen has one allowed pattern for its single electron. Helium has two. Carbon has six. Each element is characterized by the arrangement of these standing waves and by how they combine to form molecules. Every property of matter, from the hardness of a diamond, to the flexibility of a metal, to the transparency of glass, to the colors emitted by heated atoms, arises from the shapes and energies of these quantum waves. This reveals something subtle and deeply beautiful about the structure of the universe. The solidity of the world, the stability of matter, the behavior of atoms all emerge from patterns of probability, from waves that never stop evolving, waves that fill the microscopic world, waves that define what is possible, long before the particle chooses an outcome. It is remarkable that this wave-like nature is so hidden from everyday experience, and yet so fundamental to everything that exists. In the macroscopic world, wave-like spreading is negligible. A baseball's wave function spreads by an amount smaller than an atom over the lifetime of the universe. Its quantum nature exists, but it is drowned out by interactions with the environment, repeated disturbances that continually collapse its wave function and force it into classical behavior. But when a system is isolated, gently, carefully, precisely, the wave reveals itself again. It spreads, it interferes, it behaves exactly as the laws of quantum mechanics predict. You can observe this in electrons, in photons, in neutrons, in atoms cooled almost to absolute zero, in entire molecules with hundreds of atoms, all of which display wave-like interference when isolated. The wave does not depend on size, it depends on coherence. Coherence is the ability of a quantum system to maintain its wave-like properties, its phases, its interference patterns without being disturbed. When a system interacts with the environment, coherence decays. The wave loses its clear phase relationships. Interference vanishes. Classical behavior emerges. This transition from coherent waves to classical particles is one of the deepest ideas in physics and will be explored in its own section later. For now, the important insight is that the wave is always present, always fundamental, always shaping outcomes behind the scenes. The wave function guides the particle. But what does it mean to be guided? The answer lies in the mathematics of the wave. The probability of finding a particle at a given location is proportional to the square of the amplitude of its wave function at that location. This rule, known as the Born rule, connects the mathematical wave to physical results. Where the wave function is large, the particle is more likely to appear. Where the wave function is small, the particle is less likely to appear. Where the wave function is zero, the particle will never appear. These rules determine the outcomes of every experiment. They explain why interference patterns emerge. They explain why certain energy levels are allowed and others forbidden. They explain why chemical bonds have the shapes they do. They explain why tunneling occurs, why photons can be absorbed or emitted, why matter behaves predictably, despite being built on probabilities. The universe does not replace determinism with chaos. It replaces determinism with a deeper, more subtle, more flexible structure. This structure is the wave function. You can imagine the wave function as a map, a vast map of all possible futures, each point weighted, each path assigned a probability amplitude, each potential outcome encoded in the mathematics that governs evolution. The particle does not traverse all these paths physically. It does not split. It does not smear itself across space like paint. It simply remains in a state of possibility until an interaction selects one of these possibilities. This selection is governed by the wave function. It is not random in the chaotic sense. It is random in a constrained sense, a sense where the wave defines the likelihood of each outcome. This mixture of wave-like evolution and particle-like events gives rise to a world that is both unpredictable in detail and perfectly predictable in statistics. The quantum wave predicts the probabilities with astonishing accuracy, but it cannot predict which outcome will occur in a single trial. This is not a limitation of measurement. It is the nature of reality at the smallest scales. And yet, even this uncertainty feels calm, almost soothing, because the wave provides structure, guidance, a mathematical rhythm that ensures the world behaves consistently. Imagine tossing a stone into a pond. You cannot predict exactly where every drop of water will fall, but you can predict the pattern of ripples. You can predict the shape of the waves. You can predict how the disturbance will evolve. The quantum world is similar. The outcomes of individual events are uncertain, but the evolution of the wave is precise, mathematically perfect, a ripple of probability governed by the equations of motion. These ripples interact, combine, sometimes creating bright regions of probability, sometimes creating dark regions where outcomes cancel. The world is shaped by these patterns, by this delicate interference, by the silent structure of the wave function. You might imagine a single electron drifting through space, its wave function expanding outward, touching regions of possibility, bending around obstacles, forming ripples of probability that reflect the structure of the environment. The electron does not move like a classical particle. It moves like a wave, and yet, when you detect it, it leaves a single point of impact. This dual nature is not contradictory. It is complementary. It reveals that the electron's journey is guided by the wave, while its arrival is a particle-like event. The wave is the story of the journey. The particle is the story of the arrival. Both stories are true. Both are necessary. Both reflect the deeper reality of the quantum world. And as you drift deeper into this understanding, you begin to feel the quiet coherence of the whole structure, the way wave-like probability and particle-like events interlock seamlessly, forming a description of nature that is both strange and precise, both abstract and grounded, both dreamlike and analytical. This is the doorway, the soft transition into the next idea. The idea that the quantum wave, beautiful on its own, reveals its full nature only when we watch it interfere with itself. In the next continuation, we move toward the most iconic demonstration of that interference, the experiment that reveals the wave most clearly, the experiment that shows how deeply possibility shapes reality. As you drift deeper into the idea of the quantum wave, another layer of strangeness begins to reveal itself, a layer that is gentle yet fundamental, and it is the idea of superposition. Superposition is the quiet principle that a quantum system can occupy many possible states at once, not because it is switching rapidly between them, and not because it is uncertain in a classical sense, but because its wave function contains all the allowed possibilities at the same time. This is not an exaggeration. It is not metaphor. It is the literal structure of the wave. The wave does not pick one path or one configuration or one location. It holds all possibilities simultaneously, each weighted with its own amplitude, each carrying its own phase, each capable of interfering with the others. You can imagine it gently, like a chord played on a quiet instrument. Not a single note, but multiple tones resonating together, not yet resolved, not yet collapsed into a single outcome, simply existing in layered harmony. A particle in superposition is similar. Its wave holds many futures at once, many positions, many paths, many configurations, all coexisting in a mathematical structure that feels both strange and beautifully calm. This is why the electron around an atom does not orbit like a planet. It exists in a superposition of many wave patterns, many harmonics, all of which combine to form the final standing wave. The electron is not in one location. It is in all allowed locations, weighted by the wave function, until an interaction forces a choice. Superposition is not the chaotic idea it first appears to be. It is not disorder, it is structure. A structured blend of possibilities, each shaped by the system's energy, each constrained by the environment, each evolving according to precise equations. Even the idea of a particle traveling through two paths is a superposition. The wave does not choose one path, it explores both, and those paths remain present within the wave function, interfering gently, guiding the particle's future, until a measurement collapses the superposition into a single realized outcome. Classical intuition breaks down here, because classical intuition insists that reality must already be decided, that the world must commit to one configuration at all times. But the quantum world does not rush to commit. It allows possibilities to coexist, to evolve, to overlap, to interfere, and only when the system interacts strongly with something else does the superposition collapse into a definite state. The collapse is not violent. It is not abrupt in feeling. It is simply the quiet resolution of possibility into reality, like a soft wave settling onto a shore. And the origin of these possibilities lies in something even deeper, the landscape of potentials. In quantum mechanics, every region of space has an associated potential energy, a shape, a contour, a structure that guides how the wave evolves. A steep potential pushes the wave back. A shallow potential allows it to spread. A well-shaped potential can trap the wave, forming quantized energy levels like a bowl that supports only certain standing wave patterns. Even empty space has a potential structure, defined by boundaries, fields, and the geometry of the environment. The wave function responds to this structure automatically, not through conscious choice, but through the fundamental equations that determine its evolution. It is this response to potential that creates the astonishing behavior seen in atoms, where electrons occupy only certain energies, certain shapes, certain superpositions, because the potential created by the nucleus and other electrons allows only those solutions. Classical intuition fails here because classical mechanics treats energy as continuous, positions as definite, paths as unique. But the quantum world is not built from definite paths. It is built from allowed states, allowed superpositions, allowed patterns of possibility. These patterns are delicate. They depend on symmetry, on boundary conditions, on the structure of space, on the presence or absence of other particles. Even a slight change in potential can reshape the wave function, altering the probabilities, changing the allowed outcomes, shifting the superposition into a new configuration. This sensitivity is not fragility, it is precision. The wave function responds with mathematical exactness, creating a world where behavior is defined by equations, not by intuition, yet appearing to us as stable matter, stable atoms, stable molecules, all of them held together by waves of possibility. This understanding helps make sense of why electrons can never fall into the nucleus. Their allowed standing waves prevent it. The lowest energy wave function still has finite size, still has shape, still occupies space around the nucleus, still forms a probability cloud that cannot collapse beyond certain boundaries. The electron is not prevented from falling inward by a force, but by the geometry of the wave itself, a geometry rooted in the uncertainty between position and momentum, which we will explore soon. For now, it is enough to feel the gentle truth that the stability of matter arises from superposition, from probability waves settling into allowed shapes, from the quiet refusal of electrons to occupy identical states. These patterns are everywhere, in the light emitted by atoms, in the colors of the world, in the structure of solids, in the behavior of heat, in the properties of lasers, in the way metals conduct electricity, in the interactions that allow chemical reactions to occur. Every one of these phenomena depends on the quantum wave, on the superposition of possible states. on the way potentials shape those states, on the way interference determines allowed and forbidden outcomes. And perhaps the most surprising thing is that these waves behave as waves even when no one watches, even when no detector measures them, even when particles travel alone, one by one, as quietly as possible. When many possibilities exist, the wave holds them. When paths are available, the wave explores them. When boundaries appear, the wave responds. And only when the wave is disturbed does the particle collapse into a single realized state. This interplay between the wave of possibilities and the moment of realization is the heart of quantum mechanics. It is where reality feels most unfamiliar and yet most elegant. And now, with all of this gently settled, the story of the quantum wave has brought us naturally, softly, to the doorstep of the most iconic experiment ever devised, an experiment where superposition becomes visible, where potentials shape outcomes dramatically, where classical intuition breaks down completely, and where the wave shows its presence with unmistakable clarity. The next part of this journey is that experiment, the double-slit, where the quantum wave reveals its deepest truth in patterns of light, patterns of matter, patterns of possibility. And so you drift forward, carried by the wave, into the next chapter of this quiet exploration. The deeper you move into the quantum world, the more every idea leads you gently toward one experiment, one demonstration that stands like a quiet doorway into the strangeness of the small. It is simple, almost childlike in its design, yet it reveals more about the nature of reality than almost anything else discovered. You can picture it softly, a flat barrier, a source of particles, a screen where those particles land. Nothing more, nothing complicated, only the essentials. A source that sends out something tiny, electrons, photons, neutrons, atoms, even large molecules if cooled enough. A barrier with two narrow openings, and behind it, a screen that records each arrival, each point of impact, each particle's final choice. If the world behaved the way classical intuition expects, if particles were simply particles traveling along a single path, choosing one slit or the other, the result would be straightforward. Two bright regions on the screen. Two clusters of impacts, nothing mysterious. But this is not what happens. Even when the particles arrive one at a time, with long gaps of silence between them, even when each individual particle leaves a single dot on the screen, the overall pattern that slowly emerges is not two bright regions. It is a pattern of alternating light and dark bands, a pattern of interference, a pattern created by waves. It seems impossible. Each particle arrives as a single point, a tiny impact, a localized event. But when many such events accumulate, they form a pattern that only waves can create. Bright regions where waves reinforce, dark regions where waves cancel. The particle behaves like a wave until the moment it is detected, and then it behaves like a particle. Both behaviors are part of the same reality, not in conflict but intertwined, woven into the same description of the small. You can imagine sending electrons toward the barrier, one after another. The first arrives, a single dot, the second, another dot. Hours pass, days pass, each electron landing alone, never interacting with the others. But slowly, very slowly, the interference pattern appears. Where the wave function has high probability, more dots gather. Where the wave function has low probability, fewer appear. Where the wave function is zero, none appear at all. The electron reveals its dual nature, a wave that guides a particle that arrives, a wave of possibility, a particle of actuality. The double-slit experiment shows this duality with complete clarity. It does not hint, it does not suggest, it demonstrates. The wave explores both slits. It passes through both openings at once, spreading, overlapping, interfering with itself. The particle does not choose a slit. The wave makes that choice unnecessary. The wave spans the entire region, and the particle follows the probabilities the wave creates. But the mystery deepens when you try to observe what happens. If you place a detector at the slits, a gentle device to determine which slit the particle passes through, the interference disappears, completely, instantly, as though the wave has withdrawn, as though the universe has changed the rules. The pattern collapses into two bright regions, exactly what you would expect if particles were simply particles. The act of observation, the act of acquiring which path information, eliminates the interference pattern. This happens even if the detector's information is never used, even if no one looks at it, even if the data is erased before anyone can view it. The mere existence of the information, the possibility of knowing, destroys the wave-like behavior. This sensitivity is not psychological. It is not based on human awareness. It is based on interactions, on the exchange of information at the quantum level, on the way measurement entangles the particle with the measuring device. When the particle becomes entangled with the detector, its wave function collapses into a definite path. Superposition ends. The two-path wave becomes a one-path result, and without two paths, there is no interference. The pattern vanishes. Classical intuition returns, not because particles chose to behave classically, but because observation forced them into classical behavior. It is as though the quantum world allows many paths, many futures, many possibilities, until something interacts strongly enough to restrict the options. Measurement is not merely reading a pre-existing fact. Measurement helps create that fact by collapsing the wave of potential outcomes into one realized event. You can picture it gently, a soft wave spreading through the two slits, rippling outward, crossing itself, forming delicate patterns, until a detector touches it, alters it, forces it to resolve. The wave narrows, the possibilities shrink, and the particle follows a single path. This idea becomes even more mysterious when using particles that are sent one by one, because it means each particle behaves as if it interferes with itself. It means the wave function spans both slits, regardless of how slowly the particles arrive, regardless of whether they interact with one another. The wave function is not limited by the particle count. It belongs to each particle individually, even when isolated. To make this visualization clearer, you can imagine a single electron heading toward the barrier. Its wave function approaches the slits, and at the moment of encounter, the wave splits into two parts. One part passes through the left slit, the other through the right. The two parts diverge, propagate, and then overlap again beyond the barrier. Where their phases align, the combined amplitude grows. Where they oppose, the amplitude shrinks. This overlapping creates the interference pattern, and the electron, when finally detected, appears at a point that reflects these amplitudes. It does not appear randomly in the classical sense. It appears randomly within a structure created by the wave, a structure shaped by possibility, a structure shaped by interference, a structure shaped by the presence of both slits. If you close one slit, the wave no longer divides. There is no interference. The arrival pattern changes. The world becomes simpler. But when both slits are open, the wave expands its influence, its geometry, its range of futures, and the pattern becomes rich again. It is difficult to accept this if you cling to classical intuition. Classical intuition insists that particles must take one path. It insists that reality must always be definite. It insists that the world must behave consistently whether or not anyone observes it. But the quantum world does not obey those demands. It obeys the mathematics of wave functions, the rules of amplitudes, the deep structure of superposition, and the relational nature of measurement. The double-slit experiment exposes this relational nature in the clearest possible way. When no which path information exists, the wave behaves freely, and the system retains coherence. When which path information becomes available, coherence collapses, interference vanishes, the behavior changes. It is not the act of watching with eyes, but the presence of information that matters. Information is physical. Information flows through interactions. Information determines what states remain possible and what states collapse. This is why even a tiny disturbance, a photon bouncing off the particle, can destroy the interference pattern. The disturbance carries information away, entangling the system with the environment and forcing the wave to resolve. You might wonder, does the universe somehow know when it is being observed? Not in a conscious sense, not in a psychological sense, but in a physical sense. Yes, the universe responds to the availability of information. It responds to interactions. It responds to entanglement. It responds to the exchange of energy and momentum. These responses are built into the mathematics. They are not optional. They are not mysterious in the supernatural sense. They simply reflect how measurement works in a universe governed by quantum laws. The double-slit experiment reveals a profound truth about the small, a truth that is easy to state, yet endlessly rich in meaning. When possibilities remain undisturbed, they coexist, they interfere, they create structure, they form patterns. But when possibilities are disturbed, when which path information becomes encoded in the environment, the possibilities collapse. Only one remains. The others disappear, not because they were fictional, but because the wave that sustained them has been altered. And it is here, in this quiet interplay between possibility and information, that the quantum world shows its deepest character. It is not chaotic, it is not magical, it is not incomprehensible. It is simply governed by rules that differ from the rules of the large, rules where probability waves shape reality, where information determines what outcomes remain open, and where measurement is not a passive act, but an active interaction that changes the system. As you relax into this understanding, you may feel a gentle sense of awe, a sense that the universe's smallest behaviors, its tiniest motions, its most delicate patterns, are guided by laws that are subtle, precise, and deeply intertwined with the nature of knowledge itself. And this soft realization brings you naturally, quietly, toward the next idea, the idea that beneath the double-slit experiment, beneath the interference patterns, beneath the collapse of the wave, lies a more fundamental principle. The principle of uncertainty, the unavoidable blur in the foundations of the small, the idea that some aspects of reality cannot be known together, not because measurements disturb them, but because the world itself does not allow both properties to exist with perfect clarity. But that idea belongs to the next section. For now, the double slit stands as the doorway, the soft reminder that the quantum world is built from possibilities, guided by waves, shaped by information, and revealed through patterns of light and matter that gently whisper the true rules of the small. The more gently you think about the double slit experiment, the more its strangeness begins to settle into something calm, almost serene, as if the universe is quietly tin about the limits of expectation and the deeper structure beneath what seems solid. Because the experiment does not simply show interference. It shows that interference is the natural behavior of the quantum world, and that classical behavior is the exception, the rare case, the special situation that emerges only when information becomes available. The quantum world prefers possibility. It prefers superposition. It prefers the richness of many futures overlapping, as long as nothing forces it to choose. This preference becomes clearer when you imagine altering the experiment gently, changing small details, adjusting how the wave is disturbed, observing what happens when interactions occur at different strengths. If you place a detector that watches the left slit, even if it is imperfect, even if it is weak, the interference pattern begins to fade. Not instantly, but gradually, as though the wave is losing its coherence. A strong detector destroys the pattern completely. A weak detector blurs it. A vanishingly gentle detector, barely present, barely interacting, still changes the pattern. Because even the slightest entanglement between particle and detector begins to carry away information. The quantum world is sensitive to information, because information is part of the physical world. It is encoded in interactions, in correlations, in the exchange of momentum and energy, in the alignment between systems. Information is woven into the mathematics of wave functions, and the double-slit experiment reveals how deeply that weaving goes. The moment information becomes available, even if no one reads it, even if the data is never stored in a human sense, the wave function changes. It collapses into a form that no longer supports interference, because interference requires ignorance. When the universe can distinguish between the paths, even in principle, the interference disappears. When the universe cannot distinguish, even in principle, the interference returns. This subtlety is one of the deepest ideas hidden in the experiment, the idea that interference is not about physical waves hitting one another, but about indistinguishability. When two paths cannot be told apart, their amplitudes interfere. When two paths become distinguishable, no matter how gently, the interference fades. This is not philosophical, it is physical. It is encoded in the mathematics of amplitudes. And it tells us that reality at the smallest scales is not shaped by the paths particles take, but by the information available about those paths. This insight becomes even more striking when you imagine performing the experiment not with electrons, but with photons, particles of light that behave with the same blend of wave and particle, the same superposition, the same sensitivity to information. A photon's wave function spreads through both slits, interferes with itself, and produces bright and dark fringes. But if you place a detector that can determine which slit the photon passed through, even if that detector only interacts by absorbing a tiny bit of polarization information, the interference vanishes. Light loses its pattern, the fringes flatten, the distribution becomes simple, as though the wave never existed. And then, one of the most extraordinary features of the experiment emerges. You can erase the witch path information. Not just ignore it, erase it, remove it from existence, undo the possibility of knowing. If the witch path information is erased before the final detection, the interference pattern returns. The universe behaves again as though the photon passed through both slits. The waveform reforms, the fringes reappear. Even though the photon has already traveled through the slits, even though it has already interacted with the apparatus. This is the quantum eraser. And it shows that the universe does not behave based on what happened, but based on what can be known. If the paths are indistinguishable, the wave function includes both, and interference emerges. If the paths are distinguishable, the wave function collapses and interference disappears. If the distinguishability is erased, the interference returns. These behaviors are not contradictions. They are the natural consequences of how amplitudes combine, how probabilities evolve, how information shapes the quantum world. You can think of it softly, as though the universe asks a quiet question each time a particle travels. Are the paths distinguishable? And depending on the answer, the wave behaves accordingly. If the answer is no, the wave remains wide, superposed, capable of interfering. If the answer is yes, the wave narrows, collapses into a definite path. If the answer was yes, but then becomes no, the wave regains its coherence, and the interference reappears. This flexibility, this dependence on information rather than force, is one of the most subtle aspects of quantum theory. It suggests that reality at the smallest scales is relational, not fixed, not rigid, not absolute in the classical sense, but dependent on the relationships between systems, the correlations between particles, the information encoded in interactions. When you think of the world this way, the double-slit experiment becomes more than a demonstration. It becomes a window into a universe where possibility matters, where relationships shape outcomes, where ignorance allows patterns to form, and knowledge collapses them. This is not mystical. It is mathematical. It is testable. It is repeated in laboratories every day. It is confirmed across countless experiments. The double-slit experiment is repeated with such consistency, such reliability, such quiet precision, that its lessons can be trusted more deeply than almost any intuition we bring to it. It shows that the universe does not operate according to simple pictures, not according to solid objects traveling through definite routes, not according to the expectations we inherit from the macroscopic world. It operates according to waves of amplitude, waves that evolve according to strict equations, waves that combine when possibilities cannot be told apart and collapse when information flows into the environment. This is why the experiment feels so dreamlike, yet so exact. Its strangeness is not chaos, it is structure. A quiet structure that reveals itself through patterns, patterns that are subtle enough to seem unreal, yet repeatable enough to feel inevitable. The deeper you observe the experiment, the more you notice that the interference pattern is not merely decoration. It is the physical fingerprint of the wave function, a visible trace of invisible mathematics, a soft imprint of how possibilities overlap. Each bright band on the screen corresponds to constructive interference, where the phases of the wave align, where the probability of arrival increases. Each dark band corresponds to destructive interference, where the phases oppose, where the probability falls to zero, where the particle will never be found. The darkness of the dark bands is especially striking. It is not low probability, it is zero probability, a complete cancellation of possibility. The wave function prohibits arrival in those regions. No matter how many particles you send, no matter how long the experiment runs, no particle will ever land in the places the wave forbids. This reveals something profound, something almost poetic. The idea that absence is as meaningful as presence. The dark spaces are patterns too. They are shapes carved by the wave's evolution, regions where the universe has silently ruled out certain futures, not because of force, but because of interference. The double-slit experiment shows that the quantum world is full of subtle rules like this. Rules that do not announce themselves loudly but reveal themselves through careful observation, through the gentle accumulation of evidence, through patterns that appear only when you look slowly, patiently, softly. And then as you think more gently about what the experiment is actually telling you, a deeper question emerges. A question that quietly challenges the very structure of reality. How can a particle interfere with itself? It seems like an impossible question, because classical intuition demands that a particle is a single object with a single path, with a single history. But this demand is not honored in the quantum world. The wave function does not describe a single path. It describes all allowed paths, superposed, combined, evolving together. The particle does not commit to one path until forced to commit. The wave explores everything the geometry allows. This idea becomes even more striking when the experiment is performed with very large molecules. Molecules containing dozens of atoms, hundreds of atoms, sometimes over 1,000 atoms, all cooled to isolate them from environmental disturbance. These molecules are undeniably classical in size, large enough to detect with precise instruments, yet their wave functions still spread, still interfere, still form fringes on the screen. This means the strange behavior of the double slit is not limited to the smallest particles. It is universal. It applies to everything. It applies to every object in the universe, if only the conditions allow it, if only coherence can be maintained, if only information does not leak away, if only the system remains isolated. This universality leads to a gentle but unavoidable truth, a truth rarely felt in everyday life, but always present beneath the surface. The world you experience as solid and classical is simply the world that has lost coherence. It is the world where information is constantly leaking, where interactions are constant, where superpositions collapse almost instantly, long before they can interfere. Large objects do not behave quantum mechanically, not because the laws change, but because the environment forces them into definite states. The double-slit experiment reveals this beautifully. It shows that quantum rules are always present, and classical rules are the result of interactions. The world behaves classically only when the wave functions of large systems collapse too quickly for interference to survive. And so the experiment teaches two things at once. It teaches that particles behave like waves, and it teaches that waves can collapse through the flow of information into the environment. This interplay between coherence and collapse is not noisy. It is not violent. It is calm, gradual, a natural part of the quantum evolution of all systems. To see this interplay more clearly, you can imagine modifying the double-slit experiment in delicate ways. For instance, slightly warming the environment around the slits. The interference pattern begins to blur, softly at first, then more dramatically, as thermal vibrations carry information away. Or imagine placing a gas near the slits. Occasional collisions between gas molecules and the particle destroy coherence. The interference fades. The bright and dark bands flatten, becoming two broad humps, the classical pattern. Or imagine shining a faint light near the slits. If photons scatter off the passing particle, they carry which path information away. Interference collapses. In every case, the wave function has not been physically blocked. It has not been interrupted in a classical sense. It has been entangled with the environment. Information has leaked out, the paths have become distinguishable, and the wave loses the ability to interfere. This reveals something almost delicate, a principle hidden inside the mathematics. Interference is a privilege of ignorance. Only when the universe lacks information can the wave remain coherent, wide, superposed. Only when the environment has no path data can the wave explore multiple futures. Only when nothing marks the particle's history can the pattern form. The moment information becomes available, the universe commits. The wave narrows. The futures collapse. The particle chooses a path. This dependence on information does not mean consciousness affects the result. It does not require observers in the human sense. It simply requires physical interaction. Any interaction capable of leaving a trace, any exchange of energy that distinguishes possibilities. In this way, the double-slit experiment is not just about slits or screens or particles. It is about the relationship between possibility and information, between coherence and interaction, between what might happen and what becomes real. These reflections lead naturally to an even deeper question, one that gently guides you toward the next section. If a particle can never have both a definite path and an interference pattern, if the act of gaining path information destroys the wave, then what does this say about what can be known? What does it say about the limits of precision? What does it say about the nature of measurement and the idea of certainty itself? And so, as the double-slit experiment settles softly in your mind, a new idea drifts forward, the idea that the quantum world contains fundamental limits, limits not imposed by instruments, but by the structure of reality. The idea that some pairs of properties cannot both be known with perfect clarity, because the wave that defines them cannot support such certainty. This gentle truth, this unavoidable blur, is where the journey moves next, into uncertainty, into the limits of knowing, into the quiet principle that reshapes our understanding of what reality allows. The double-slit experiment becomes even stranger when we look deeper into the role of information, not interference, not measurement in the everyday sense, but the simple presence or absence of knowable facts. In quantum mechanics, it is not the detector's physical size that matters, nor the material it is made of, nor even whether it clicks or flashes or records a number. The essential ingredient is whether the universe could, in principle, distinguish one path from another. If the two paths through the slits remain identical in every observable way, the wave of possibility stays whole, undivided, free to overlap with itself. The interference pattern forms with serene precision, bright bands and dark bands emerging from nothing more than the quiet mathematics of the wave function. But the moment any trace exists, any correlation, any mark upon the environment that could reveal which slit the particle traveled through, the delicate wave is forced into a single history, a definite path, a committed trajectory, and the interference disappears. What makes this so astonishing is that it does not matter whether anyone looks at the information. The detector can be switched on, but the reading ignored. The result is the same. The interference fades. The wave does not wait for a human mind. It responds to the mere availability of knowledge in the physical world. This is one of the deepest lessons of the experiment, a lesson that continues to unsettle even the most seasoned physicists. Reality at small scales is intertwined with information in a way that defies classical thinking. The universe behaves differently depending on what can, not what will, be known. Imagine a photon traveling toward the slits, its wave function stretching like a soft mist, flowing around both openings, pressing into the region beyond. Now imagine placing a particle of dust near one of the slits, so small that no human detector could ever notice it, but large enough that a grazing interaction with the photon might shift its quantum state ever so slightly. If the dust could, even hypothetically, reveal the photon's path by altering its own state, the interference vanishes. The photon behaves as though it traveled through one slit or the other. The dust grain becomes an accidental witness, a cosmic observer with no eyes, no awareness, no intention, yet its presence changes the outcome. This reveals a profound principle, one that feels almost philosophical, but is grounded firmly in the equations. Every interaction creates a connection between systems, a flow of information, and that information influences how the wave function evolves. The universe does not require a conscious observer, only a physical record. In the quantum world, information is not abstract. It is as real as mass or charge or spin. It shapes the behavior of particles. It determines whether possibilities blend or separate or collapse into definite outcomes. And so the double-slit experiment becomes not just a puzzle of patterns, but a story about the deep structure of physical law, a story in which the presence of knowledge shapes the very fabric of events. This is why the experiment is often described as the heart of quantum mechanics. It reveals that nature does not behave like a collection of tiny billiard balls bouncing through space. It behaves like a tapestry of overlapping possibilities, a shifting sea of probability waves that sometimes interfere and sometimes do not, depending on whether the world permits those possibilities to coexist. When the paths are indistinguishable, the waves blend, and the universe expresses the full richness of superposition. When the paths are distinguishable, the waves retreat into singular outcomes, as if the act of differentiation collapses the shimmering field of potential. This interplay between possibility and information is subtle, but essential. It shows us that the quantum world does not choose a definite history until forced to. The forcing can come from a measuring device, a stray molecule, a slight interaction with the environment, or even a hypothetical correlation that no one will ever actually access. In this way, the universe is continuously determining what can interfere with what. It is continuously deciding which paths are compatible, which histories remain entangled, and which become irrevocably distinct. This is why even a single particle, fired one at a time, can build up an interference pattern. Each photon, each electron, each neutron travels through the slits as a wave of probability, spread out, delocalized, reaching through both openings at once. Its detection on the screen appears as a single dot, a small bright mark, a definite event. But over many repetitions, the dots arrange themselves into a wave pattern, a quiet testament to the deeper structure beneath each individual landing. This is not behavior imposed by groups of particles. It belongs to the single particle itself. It carries its own wave function, its own internal landscape of probability, its own capacity to interfere with itself. This leads to a natural question, one that physicists have asked for more than a century. What collapses the wave function? Some interpretations say that collapse is not a physical event, but a change in our description, a shift from one mathematical tool to another. Others say collapse is real, a genuine physical transition, a sudden snap from a superposition to a single outcome. And still others say that all possible outcomes occur, just not in the same branch of reality. The double-slit experiment does not settle these debates, but it gives them shape, it gives them weight, it gives them the quiet gravity of direct evidence. Whatever the underlying truth may be, one fact remains firm. The wave function behaves differently when paths are distinguishable. Information changes the evolution of the system, even when the information is never read. Imagine now a different twist on the experiment, the delayed choice setup. Here, the experimenter can decide whether to preserve or destroy the interference pattern, even after the particle has passed through the slits. It sounds impossible, but the mathematics predicts it cleanly, and the experiments confirm it. If the setup allows the paths to remain indistinguishable, the interference appears. If the setup reveals which path the particle could have taken, the interference vanishes. This happens even when the decision is made so late that no classical signal could reach the slits in time. It is as if the universe does not commit to a single history until all the relevant information, past, present, or future, is considered. This does not allow communication backward in time. It does not violate causality. But it does show that the wave function's evolution is not a simple chronological process. It reflects relationships between events, not the order in which they occur from a human perspective. The particle does not travel in a classical trajectory, carrying with it a hidden answer to the question of which slit it passed through. Instead, the entire experimental arrangement determines which description of reality is valid, wave-like or particle-like, interfering or collapsing. The system behaves as a whole, not as a sequence of isolated moments. This is why the double-slit experiment is more than a demonstration of strangeness. It is a window into the logical structure of quantum theory, a theory in which probabilities are not about ignorance, but about the fundamental nature of the small. The photon is not secretly a particle with a definite but unknown path, nor is it secretly a wave with a definite but hidden amplitude distribution. It is a quantum object, whose identity depends on the circumstances of the measurement, on the informational context, on the structure of the experiment itself. And so, the double-slit experiment becomes a meditation on the fluidity of reality. It shows that the universe at the smallest scales is not divided cleanly into particles or waves, but moves between them according to deeper rules written in the language of probability, superposition, and information. The more we look, the more the experiment seems to whisper a simple truth, that reality is not built from rigid pieces, but from patterns of likelihood, delicate, shifting, responsive to the quiet presence of knowledge. As we drift deeper into this understanding, we begin to feel a kind of calm. Quantum mechanics does not demand that we intuitively grasp these behaviors. It only asks that we notice the pattern, that we see the structure behind the strangeness, that we let go of classical expectations long enough to appreciate the beauty of possibility. The double-slit experiment is the gateway to that appreciation. It invites us to witness the dance between what is known and what is possible. It invites us to rest within the mystery without needing to solve it tonight. And as the final ripples of its interference fade gently into thought, we can feel the next topic approaching, a quiet horizon coming into view. The idea that uncertainty is not a flaw in our perception, but a feature of the universe itself, a fundamental limit on what can be known and what can be predicted, and how sharply reality can be described, a soft drift from interference into uncertainty. There is a point in the quantum world, a quiet threshold, where certainty dissolves into something softer, something more fluid, something that refuses to be pinned down no matter how carefully we try. This is the realm of uncertainty, not as confusion, not as human limitation, but as a built-in property of nature, woven into the mathematics, woven into the structure of space and time, woven into the smallest motions of the universe. In the classical world, we are used to the idea that objects have definite positions, definite velocities, definite trajectories, even if we do not happen to know them. A baseball thrown across a field has a precise speed, a precise direction, a precise location at each moment. Our ignorance does not change the baseball's reality. But in the quantum world, this intuition does not survive. Electrons do not travel like tiny pellets. Photons do not glide like miniature beads of light. Atoms do not orbit their centers like planets circling a star. Instead, they exist in a space where certain pairs of properties cannot be simultaneously defined. A space where knowing one thing sharply blurs the other. A space where precision always leaves a shadow. This idea emerged from a simple insight that waves are spread out and particles are localized, and quantum objects, being both wave and particle, cannot satisfy both properties at once. The uncertainty principle is not a technical obstacle. It is a fundamental symmetry of the world. If you try to measure the position of a particle with infinite accuracy, its wave function must collapse into a sharp spike, a pinpoint, a concentrated peak in space. But a perfectly localized wave is made from an infinite mixture of wavelengths, and those wavelengths correspond to momentum. So a sharply localized particle has an uncertain momentum. It can move in any direction, with a wide spread of possible velocities. Conversely, if you try to measure a particle's momentum with perfect accuracy, its wave function must stretch out in space, long and smooth, spread over great distances, erasing any precise information about where it is. This interplay is not a trick of the equations. It is not caused by the disturbance of measurement. It is not the universe hiding information from us. It is the universe expressing what it is. A quantum object simply does not possess a perfectly defined position and a perfectly defined momentum at the same time. One becomes sharper as the other becomes softer. The two properties trade clarity, as if the universe is balancing a quiet equation between what can be known and what must remain unresolved. Heisenberg's relation captures this in a graceful inequality, but the deeper truth lies in the wave nature of matter. A narrow wave in space demands a wide wave in momentum, and a narrow wave in momentum demands a wide wave in space. These are not limits placed upon us. They are limits within reality itself. If we look into the quantum world with patience, we begin to see how uncertainty shapes everything. The electron inside an atom does not orbit in a tiny circle. It exists as a cloud of probability, a region where it is likely to be found, and regions where it is not. The cloud is shaped by the balance between potential energy, kinetic energy, and the constraints of uncertainty. If the electron tried to collapse into a tiny point near the nucleus, its position would be sharply known, but its momentum would spread wildly, making it unstable, forcing it outward again. The structure of atoms is built upon the quiet tension between localization and delocalization, between the pull of the nucleus and the push of uncertainty. This tension is the reason atoms do not collapse. It is the reason matter occupies space. It is the reason the physical world has size, texture, shape. Uncertainty is not chaos, it is architecture. And when we look even smaller, the idea becomes more pronounced. Every particle in the universe, even those at rest, even those isolated in deep vacuum, possesses a small degree of jitter, a flicker of energy, an irreducible trembling. This trembling is not caused by heat or motion or environment. It comes from the uncertainty principle itself. Position and momentum cannot both settle perfectly, so even a particle in its lowest energy state, its quietest state, its ground state, cannot be completely still. The entire quantum world hums with this residual motion, a soft background vibration, like the faintest cosmic breath. If we look even deeper, to the level of fields, we find that this uncertainty manifests as vacuum fluctuations, tiny momentary pulses of energy that rise and fall, appear and vanish. A restless shimmer woven into the very emptiness of space. This shimmering is not noise. It is the unavoidable consequence of the limits built into nature, limits that hold even when nothing more than pure vacuum remains. And yet, in this strange world, uncertainty does not prevent prediction. It does not erase order. Quantum mechanics is not a theory of randomness, but a theory of structured probability, patterns hidden beneath the blur. Electrons do not move randomly inside atoms. Their positions fluctuate with precise statistical shapes. Photons do not wander aimlessly. Their energy and momentum follow strict distributions determined by the conditions that created them. Uncertainty gives rise to patterns. It shapes the spectra of atoms. It defines the rules of chemistry. It controls the stability of matter. It dictates the densities of stars. It determines how light interacts with electrons, how fields propagate, how energy is stored and released. The blur is not disorder, it is law. As we drift deeper into this idea, a quiet realization emerges. In the quantum world, knowing everything is not only impossible, it is meaningless. Nature does not hide precise values behind a curtain. Those values do not exist until certain questions are asked, and when one question is answered sharply, other answers dissolve. Consider the simple act of trying to observe a particle's position. To see where it is, we must interact with it. Perhaps with a photon, a particle of light. A high-frequency photon can pinpoint the particle's location with great precision, but its energy is high, so the interaction jolts the particle, changing its momentum dramatically. This is not a flaw in our instruments. It is a consequence of the quantum nature of light and matter. The very probe used to sharpen our knowledge creates a fundamental rearrangement. But even if we imagined a perfect measurement apparatus with no disturbance, the interplay would remain. The position would gain clarity, and the momentum would blur. The uncertainty is not added by the measurement. It is exposed by it. Quantum mechanics forces us to rethink what it means to understand something. In classical physics, understanding means knowing the details, the exact numbers, the precise states. In quantum physics, understanding means seeing the structure of possibilities, how they evolve, how they interfere, how they blossom into patterns. And slowly, gently, we begin to accept that certainty is not the foundation of nature. Probability is. Structures of likelihood, not structures of absolutes, govern the small. This may sound abstract, yet it shapes the world intimately. The warmth in your room tonight, the way atoms vibrate in the air, the way electrons flow through wires, the way chemical bonds form and break, every one of these processes depends on quantum uncertainty. It gives electrons their kinetic energy. It allows atoms to resist collapse. It sets the energy levels in molecules. It establishes the rules of stability. It governs tunneling in the sun and the behavior of superconductors and the limits of measurement. Uncertainty is not a flaw. It is a quiet mechanism that allows the universe to be rich and dynamic rather than frozen in rigid precision. And there is another layer, an even more subtle one. Uncertainty does not apply only to position and momentum. It applies to many pairs of quantities: energy and time, angle and angular momentum, even the number of particles in a system and the phase of a quantum field. Whenever two properties are linked through the mathematics of non-commuting operators, one becomes sharp at the cost of the other becoming soft. Yet despite this softness, the predictions of quantum mechanics are incredibly precise. The magnetic moment of the electron, predicted using quantum rules, matches experiment to more than a dozen decimal places, a level of accuracy beyond anything in classical physics. The blur does not diminish the clarity of the theory. It enhances it. It reveals structure that would otherwise remain invisible. This paradoxical balance between definite mathematics and indefinite properties makes the quantum world feel almost dreamlike, a place where the borders between states are smooth and the edges between possibilities are soft. As we drift through this landscape, we begin to understand that uncertainty is not simply a constraint, but a gentle shaping force. It stabilizes, it structures, it defines, it sets the scale of the small, and through the small, it shapes the large. And when we listen quietly, when we let the idea settle, we may notice something else. Uncertainty is the first hint that quantum reality is not isolated at each point, but interconnected. The blurring of properties allows entanglement to form. It allows correlations to weave through space. It allows two particles to share a state in ways no classical object can. As Section 3 draws softly toward its close, we can feel the next idea rising, a natural continuation, as if the universe is guiding us gently forward. The idea that particles can become linked so deeply, so completely, that measuring one affects the description of the other, even across vast distances. A quiet thread connecting distant parts of the cosmos, a whisper of shared reality. At the smallest scales, in the quiet depths of the quantum world, there is no such thing as stillness. Even when a system sits in its lowest possible energy state, even when no heat is present and no forces seem to act on it, motion persists. Not classical motion, not the motion of a particle drifting from place to place, but a subtler motion, a trembling born from uncertainty itself. The universe, at its smallest scales, never completely settles. If we could look closely enough at a particle in its ground state, we would find that its position is not fixed, its momentum is not zero, its energy is not perfectly calm. There is a faint jitter, a soft oscillation, a permanent, unavoidable disturbance. Not because something pushes on it, but because the uncertainty principle forbids perfect rest. This constant motion, this intrinsic fluctuation, is sometimes called quantum zero-point motion. It is the quiet baseline vibration that remains even when all other energy is removed. It is not noise. It is not randomness imposed from the outside. It is the fundamental shape of quantum reality, a world where probability peaks and spreads, where position and momentum cannot both collapse into perfect clarity. And when we enlarge our view beyond a single particle to a whole field, we find something even stranger. Every quantum field, from the electron field to the photon field to the quark and gluon fields, has its own zero-point energy, its own restless baseline, its own tiny fluctuations that never die away. If we imagine space as quiet and empty, this intuition comes from classical thinking. In the quantum view, empty space is filled with activity, waves constantly forming and dissolving, virtual particles appearing and then fading, a foam of possibility, a shimmer woven into the vacuum. This foam arises directly from uncertainty. If the energy of the vacuum were fixed with perfect precision, then the time over which we could meaningfully talk about it would become undefined. Energy and time form another uncertainty pair, one that links the stability of energy to the duration over which it can be measured. So the vacuum does not hold a single precise energy. Instead, it flickers. For very short intervals, tiny wiggles of energy appear, borrowed from the uncertainty relationship, and then vanish again, returning the vacuum to its baseline average. These fleeting fluctuations shape the world in subtle ways. They shift the energy levels of atoms. They influence the behavior of electrons orbiting nuclei. They contribute to forces that draw metal plates together. They remind us that even nothing is not truly nothing. Uncertainty fills the small with motion, not chaotic motion, but patterned motion. Statistical motion, motion woven into the mathematics of how fields must behave. When we consider position and momentum uncertainty again, we see how deeply it shapes the structure of atoms. An electron does not spiral into the nucleus, not because the nucleus repels it, but because trying to confine the electron too tightly forces its momentum spread to grow, giving it enough kinetic energy to resist collapse. Uncertainty gives atoms size. It gives them stability. It gives them the structure that allows chemistry to exist, allows matter to bind, allows molecules to form, allows life to emerge. Every detail of atomic structure, every orbital, every energy level, every bond, is sculpted by the interplay between probability waves and constraints from uncertainty. If uncertainty were not real, electrons would collapse inward, atoms would be unstable, matter as we know it would vanish. The blur is not a complication, it is a foundation. And as we drift deeper into this idea, another subtle theme emerges. uncertainty is not only a statement about measurement, it is a statement about what exists. When we say that a particle does not have a definite position until measured, we are not saying that the position exists but is hidden. We are saying that the particle literally does not have a single position. Its position is distributed, spread, located only in probability until an interaction forces a specific outcome. And when we say that a particle does not have a definite momentum until measured, we mean that its momentum is also distributed, a blend of possibilities woven through its wave function. The universe at the quantum scale is not composed of sharp facts. It is composed of smooth distributions, gradients of possibility, clouds of potential outcomes. Measurement does not reveal reality. Measurement creates a particular branch of it, collapsing the probabilistic wave into one realized result. The rest of the wave, the parts that did not become actual, fade away from that moment forward. This leads to a profound reinterpretation of what it means to know something. In the classical world, knowing means discovering pre-existing values. In the quantum world, knowing means choosing which potential becomes actual. Yet even here, uncertainty is not arbitrary. It is guided by strict rules. The probability distributions are determined by the wave function, and the wave function evolves according to precise mathematics. Quantum mechanics balances softness and structure, blur and predictability, probability and pattern. To explore this balance further, we consider microscopic fluctuations. At extremely small scales, particles behave like waves in constant motion. Their phases change, their amplitudes rise and fall. Their interactions lead to ripples of likelihood radiating outward. Even when isolated, they experience fluctuations from their underlying fields. A free electron drifting alone in space does not travel in a straight line in a classical sense. Its position probability distribution spreads over time, expanding outward, becoming more diffuse. This spreading is a natural consequence of momentum uncertainty. A narrow momentum distribution would require a wide position distribution. A narrow position distribution requires a wide momentum distribution. So over time, the wave function of a free particle naturally widens. This is the quantum foam of constant motion, a gentle breathing of probability, a drift without a classical trajectory, where the wave itself is the object. If we could observe these fluctuations directly, we would see that the small is not still, not firm, not anchored. The small is inherently blurry. Its nature is one of possibilities rather than fixed states. And this blurriness is not a weakness, it is a strength. It explains why electrons can form stable orbitals. It explains why atoms have discrete energy levels. It explains why molecules vibrate and rotate with quantized energies. It explains why tunneling occurs, why superconductivity arises, why superfluidity exists, why quantum fields ripple. It even explains the stability of neutron stars, where uncertainty prevents quarks from collapsing into a single point, creating the degeneracy pressure that holds the star against gravitational collapse. The uncertainty principle is not a small rule. It is one of the fundamental pillars of reality. The deeper we look, the more we see it shaping everything. Time and energy form another pair constrained by uncertainty. The shorter the interval over which we try to measure energy, the less precisely that energy can be defined. This is why short-lived particles can arise briefly with energies that seem to violate classical conservation, only to return their borrowed energy as they vanish. These are virtual particles, fluctuations that are permitted by uncertainty, provided they exist only for very short times. The quantum foam is full of these brief appearances, tiny bursts of possibility that affect the behavior of fields, even though they cannot be directly observed. If we attempt to measure an electron's energy very precisely, the measurement must be taken over a long period of time. If we take a quick measurement, the energy becomes uncertain. This is why unstable particles have an inherent line width, a natural spread in the energies of their decay products. The shorter their lifetime, the broader the energy distribution. Uncertainty also appears in the phase and number of particles in certain systems. In a laser beam, for example, the phase is well defined, but the number of photons becomes uncertain. In other systems, the number is fixed, but the phase becomes uncertain. These are all manifestations of the same deep principle, that certain properties cannot be simultaneously and perfectly known because they are not simultaneously and perfectly defined. The world is built from these limitations, from these balances, from these trade-offs. Yet the limitations do not prevent order. They allow it. Uncertainty gives rise to stability at the atomic level, and richness at the molecular level, and structure at the macroscopic level. It shapes how stars fuse elements, how electrons arrange themselves into bands in a solid, how particles scatter, how light interacts with matter. Without uncertainty, the universe would be rigid, brittle, unable to form the structures that allow complexity to emerge. As we drift through these ideas, a soft realization begins to form. Uncertainty is not randomness. It is not chaos. It is not a breakdown of meaning. It is a deeper order, one that lives beneath the surface of classical intuition, one that offers a more subtle picture of how reality operates. And as we follow this trail, we approach the boundary where uncertainty begins to touch something even stranger. Something that hints at the interconnectedness of the quantum world, something that reveals that separate particles can share a state, a memory, a structure, even when separated by vast distances. Uncertainty creates the room for entanglement. It creates the soft boundaries that allow wave functions to merge, to overlap, to share information in ways that defy classical expectation. And through this merging, the universe begins to show us that reality is not built from isolated parts, but from relationships, from patterns, from correlations that stretch across space. As Section 3 comes gently to an end, we drift naturally into the next question, the question of how particles can share a state so deeply, so intimately, that knowing one changes the description of the other, a quiet thread connecting distant parts of the cosmos, a shared reality beneath the surface. There is a place in the quantum world where separateness begins to soften, where the boundaries we draw between one object and another, between here and there, between this and that, grow thin enough to slip through. A place where the universe reveals a strange kind of unity, not through force, not through communication, but through shared structure. This is the realm of entanglement, where particles do not carry individual stories, but participate in a single shared state, woven together even when they drift far apart. To understand this gently, we begin with the idea that a quantum state does not always belong to one particle. Sometimes it belongs to a pair, or a trio, or a whole collection. A single wave function, spread across multiple systems, binding them in a correlation deeper than anything classical physics can describe. Imagine two photons, created in the same event, born from the same ripple of a quantum field. They are not separate creations. They are two branches of one process, two expressions of one interaction, two outcomes of a single transformation. Their polarizations, their internal states, their quantum properties are connected, not predetermined, not stored in hidden variables, but linked through the mathematics of superposition. Before measurement, neither photon has a definite polarization. Each exists in a cloud of possibilities, a mixture of states, a soft distribution rather than a fixed fact. But their possibilities are not independent. The two clouds overlap, they intertwine, they form a single pattern, a shared tapestry of potential outcomes. And when one photon is measured, its cloud collapses into a definite value, and the other cloud collapses in a way consistent with the correlation that existed all along. This does not mean one photon tells the other what to do. Nothing travels between them. Nothing crosses the space that divides them. Instead, a measurement reveals part of a pattern, and the rest of the pattern adjusts to remain consistent. Entanglement is not communication, it is coherence. To picture this more deeply, imagine two electrons interacting briefly. During the interaction, their wave functions overlap. They exchange momentum, exchange spin information, exchange quantum structure. When the interaction ends, the electrons move apart. But the structure they formed together remains. It is carried with them, not as classical instructions, but as correlations written into the combined wave function. If one electron is later measured to have spin up along some direction, the other electron's spin becomes defined relative to it, even though its individual spin had no definite value beforehand. The correlation is the reality. The individual values arise only in measurement. This is the essence of entanglement, a property of the pair, not the parts. And because the correlation lives in the wave function, and the wave function is not a physical object inside space, but a mathematical object describing probabilities, Distance does not weaken the connection. Two entangled particles can drift as far apart as the universe allows and still share the same unified description. Space stretches between them, but the wave function spans that distance effortlessly because it does not reside in physical space. It resides in the mathematical space of states, a space where separation is not defined in the classical sense. When Einstein called this spooky action at a distance, he was reacting to the way the quantum world disregards classical locality. He envisioned a universe where reality at one location depends only on things in its immediate vicinity. Quantum mechanics showed him a deeper truth, that reality at one point can be intertwined with reality at another, regardless of the space between. Not through signals, not through influence, but through structure. Entanglement has been tested with extraordinary precision. Experiments measuring photon polarization correlations, electron spin correlations, atomic entanglement, superconducting qubit entanglement, all confirm that no classical explanation fits the data. Bell's inequalities, the mathematical expressions of classical assumptions about separability, are violated. Not slightly, not marginally, but decisively. The universe does not store information locally. It stores information relationally. This relational nature appears everywhere once you know how to look for it. In chemistry, electrons in molecules become entangled with one another, their orbitals forming delocalized states that span multiple atoms. These states give molecules shape, polarity, stability, reactivity. In solid-state physics, electrons in a crystal form collective entangled states that determine conductivity, semiconductor behavior, the very existence of band structure. In superconductors, pairs of electrons move together in entangled states called Cooper pairs, allowing them to flow without resistance. In quantum biology, there is growing evidence that entanglement plays a role in processes like photosynthesis, allowing energy to move efficiently across molecular structures. Entanglement is not exotic, it is ordinary, it is everywhere. It simply hides behind decoherence, dissolving quickly when systems interact with their environments. The classical world is a world where entanglement patterns are constantly washed out. Noise, vibrations, collisions, thermal interactions continually entangle systems with their surroundings, spreading quantum information into countless environmental degrees of freedom, making the original correlations impossible to recover. This is why we do not see macroscopic objects entangled in our daily experience. The connections diffuse too quickly, their delicate patterns diluted by the enormous number of particles and interactions around them. But when we isolate a system, cool it, shield it from noise, track its state carefully, entanglement becomes visible again. It emerges from the background, revealing its quiet, beautiful structure. In a well-controlled experiment, we can entangle two ions trapped in an electromagnetic field. We can cool them nearly to rest, remove external disturbances, and let their internal states intertwine. Then we can measure one and see the other respond with perfect correlation. We can entangle photons in optical fibers, send them through kilometers of cable, and still observe matching measurement outcomes at the ends. We can entangle electrons in semiconductor devices, monitor their spins, and watch their correlations unfold in time. We can even entangle distant superconducting qubits on opposite sides of a chip or opposite sides of a room, and watch them share states that remain coherent long enough to perform computations. Entanglement is a resource, a structure, a capability of the quantum world that has no classical counterpart. But beneath the technicalities, beneath the experiments and equations stands a deeper message. Entanglement invites us to rethink what it means for two things to be separate. It suggests that independence is not the default, that separateness is not fundamental, that the universe is, at its core, woven from relationships. The small does not behave like isolated points, it behaves like a tapestry, a web, a network of connected possibilities. This connectedness does not mean everything affects everything else instantly. It does not break causality. It does not violate relativity. It simply means that the quantum description of the world does not care about the boundaries we draw in space. Spatial separation is a classical idea. Quantum reality lives in a different kind of structure, a structure where correlations can stretch across the cosmos while still respecting the speed limit of information transfer. If we drift deeper into this view, We begin to see entanglement as a language the universe uses to describe composite systems, a language that encodes not the properties of isolated parts, but the relationships among them. Two spins pointing in opposite directions, two photons with linked polarizations, two atoms with paired energy states, two qubits sharing a superposition. Each of these patterns is a sentence written in the grammar of quantum mechanics. And these sentences tell a story of unity beneath separation, a story of coherence beneath distance, a story of the universe building structure not only from things, but from the invisible bonds between them. As we drift through this perspective, a gentle realization rises. Entanglement is not only a property of particles, it is a property of the universe. Whenever particles interact, even briefly, their wave functions mix. Some vestige of that mixing remains. Some trace of their shared probability structure lingers. The universe is full of these traces, threads of connection, woven into every process, every interaction, every exchange. In the large-scale world, these threads dissolve too quickly to notice, but in the small, they define everything. And as we feel the soft edges of Section 4 approach their natural close, a new question emerges, a quiet one, a question about how particles move through barriers, how they appear where classical physics forbids them, how probability waves slip through the impossible. The story of tunneling waits just beyond this moment, a continuation of everything entanglement has begun to suggest, a reminder that quantum reality does not obey the boundaries drawn by classical intuition. When physicists speak about entanglement spreading through an interaction, they often describe it as a flow of information, not classical information, not bits, not messages, but quantum information, the structure of correlations, the patterns that define how one system is related to another. These patterns are delicate. They require coherence, that quiet alignment of phases, that subtle harmony between wave functions. And yet, for brief moments, they can be remarkably robust. Two atoms separated in space can share a quantum link, holding a joint superposition that does not belong to either alone. The pair behaves as a single entity, even though each sits in a different position, blind to the other in every classical sense. The strangeness deepens when we remember that quantum properties are not rigid. Spin, polarization, energy levels, they exist in states of potential, and these potentials can be bound together. Imagine two electrons prepared so that their total spin equals 0. One must eventually be measured as spin up, the other as spin down, but before the measurement, neither possesses that value. Instead, both electrons rest in a joint superposition, a structure that says only this: whatever one becomes, the other must complement it. This is not fate. This is not pre-written outcome. This is constraint. Quantum mechanics does not fix the individual results, but it fixes the relationship between them. The universe cares less about the pieces and more about the symmetry they maintain. As you drift into the quiet logic of this, you might sense that entanglement is not merely unusual. It is revealing. It tells us that at a deep level, the world is not built from isolated building blocks. It is built from connections, from shared structures, from wave functions that bind multiple systems into a single mathematical body. And because the wave function lives not in physical space, but in a high-dimensional configuration space, the connection between systems does not fade with distance. Space stretches, atoms drift, photons fly, but the entangled correlations remain, so long as nothing disturbs them. This is why experiments send entangled photons across cities, through optical fibers twisting under streets, over open air between mountain peaks, even between satellites and ground stations. The photons race apart, yet the correlation survives the journey. If one is measured at some orientation, the pattern of outcomes for the other shifts precisely as quantum theory predicts. This does not mean the measurement outcome was already decided. It means the universe respects the structure of the joint state, a structure set not by distance but by the mathematics of superposition. And it means something else, something subtle, something that reveals the nature of information itself. In the classical world, information describes the state of things. In the quantum world, information describes the state of possibilities, and entanglement ties those possibilities together. This becomes especially clear in Bell experiments, where detectors measure correlated properties at angles chosen randomly and independently. No classical model can match the results, yet the quantum predictions fit perfectly. The violation of Bell inequalities is not a small detail. It is a profound signature. It says the universe is non-local in its structure, though perfectly local in its communication. It says the quantum world we rest upon, the one we barely sense, does not respect the classical idea that reality is built from separate pieces. Instead, reality is woven from joint patterns, joint amplitudes, joint possibilities. Each measurement is not simply a result. It is a revelation of the correlations encoded in the wave function. To understand how deep this goes, consider an entangled pair created in a process called spontaneous parametric down conversion. A high-energy photon enters a nonlinear crystal and, with a small probability, splits into two lower-energy photons. Energy is conserved, momentum is conserved, polarization constraints apply, but the details of how each photon emerges are not fixed individually. What is fixed is the total. The crystal produces pairs whose combined properties obey conservation laws, but each photon alone remains undefined until measured. This conservation-based entanglement is one of the clearest examples of how quantum mechanics ties systems together. It shows that entanglement is not magic, not a trick, not something layered on top of physics. It is the natural consequence of interactions. Whenever systems interact, their states become mixed. Whenever states become mixed, they share a wave function. Whenever they share a wave function, entanglement is born. This means entanglement is not rare. It is not exotic. It is the default behavior of the universe. It is classical separateness that is unusual and must be constantly re-established by decoherence. In the early moments after two systems interact, they remain in a fragile, beautiful superposition of possibilities. But the environment crowds in. Air molecules collide. Vibrations shake the system. Thermal photons scatter. Countless degrees of freedom gently pull the coherent state apart, spreading its correlations into a vast web of environmental interactions. This diffusion of information does not destroy entanglement. It dilutes it. It hides it. It makes the original correlations inaccessible, buried in a sea of environmental complexity. This is why macroscopic objects appear classical. Their entanglement patterns are too widely dispersed, intertwined with too many variables, to show themselves in clean, recoverable ways. Yet even as you sit here, listening, breathing softly, you are entangled with your surroundings. Your atoms exchange photons with the air. Your temperature is shared with the world around you. Your electrons interact with electromagnetic fields. The entanglement is everywhere, but hidden by scale and washed out by decoherence. In the quantum realm, where interactions can be isolated and noise minimized, the beauty becomes visible again. In superconducting qubit systems, researchers can entangle two qubits, perform controlled operations, separate them, and still observe the perfect correlations encoded in their joint wave function. In trapped ion experiments, entanglement can be created between ions held in electromagnetic cages, their motion synchronized, their internal states coupled by laser pulses, their coherence lasting long enough to perform precise computational steps. In optical setups, researchers can entangle photons encoded with multiple properties at once: polarization, phase, orbital angular momentum, creating rich multidimensional entangled states. These experiments demonstrate something simple, yet profoundly calming. The universe allows connection without contact, unity without merging, correlation without communication, structure without physical ties. It shows us that the relationships between systems can be as fundamental as the systems themselves. And as you drift deeper into this understanding, you may feel the quiet philosophical weight of it. Entanglement hints at a universe that is not a scattered collection of objects, but a continuous web, where locality is only a practical approximation and separateness is a convenience of scale. At the deepest level, the cosmos is not made of things. It is made of relationships. This realization forms a gentle bridge, leading naturally to the next chapter, where the small slips through barriers as if they were mist, where probabilities seep into forbidden regions, where the quantum wave reveals its ability to cross impossibilities. When we imagine the universe at the smallest scale, it becomes clear that the boundaries we take for granted in the macroscopic world do not truly exist. They are conveniences, emergent approximations, the result of decoherence smoothing out the delicate structures of the quantum realm. In the microworld, systems are not isolated. Every interaction leaves a trace. Every exchange of energy, every scattering of a photon, every gentle collision of particles creates a tiny bond, a thread of correlation, a faint imprint that links the participants. Entanglement is not the exception. It is the natural consequence of interaction. It is what happens when the universe allows two wave functions to intertwine, overlap, and form a single mathematical object with multiple parts woven together. This weaving is subtle. It does not require force. It does not require contact. It does not require matter to touch matter. A single interaction is enough, a fleeting exchange, a moment of shared amplitude. After that moment, even if the particles drift far apart, even if they travel kilometers, even if one races through a fiber optic cable while the other moves freely through open air, the structure of the joint wave function remains. The correlations remain. The pattern remains. The connection remains. And yet, entanglement does not allow messages to pass. It does not carry signals faster than light. It does not break relativity. What it carries is structure, not communication. Two measurements on entangled systems will show matching patterns, but no observer can choose an outcome to influence the other. The universe protects causality even as it violates classical expectations. This balance is one of the quiet marvels of physics, a universe that is deeply interconnected, yet strictly limited in what information can be sent across those hidden connections. There is something peaceful in this, something humbling. A reminder that the laws of nature are intricate, balanced, subtle, and harmonious. To explore this harmony more deeply, imagine performing a Bell experiment. Two detectors sit far apart, operated by independent experimenters who choose their measurement settings in real time, unpredictably, ensuring no signal could coordinate the choices. A pair of entangled particles is emitted, one flying left and one flying right. Each reaches its detector. Each is measured. And when the experimenters later compare notes, they find correlations that match the quantum predictions, but break every classical model based on hidden variables. The data whisper something profound, that the universe does not store definite properties inside objects before they are measured. Instead, it holds patterns of potential, relationships waiting to unfold only at the moment of observation. The experiment reveals not what the particles were, but what the quantum state allowed them to become together. As you settle into this understanding, the idea of separateness begins to soften. Space feels less like empty distance and more like a gentle backdrop against which correlations unfold. The quantum world does not care about the separation of objects the way classical intuition does. It cares about the unity of the wave function, the structure of amplitudes, the mathematical connections that exist beyond space and beneath appearance. And this is where entanglement touches philosophy, not loudly, not with conclusions, but with quiet implications. It hints that the world we experience is not the full story, that the classical picture is a surface-level description of a deeper, more intertwined reality, that locality, causality, space, and separateness are approximate, emergent, practical, but not fundamental. At the deepest level, the universe feels more like a single entity than a collection of independent parts. Each measurement, each interaction, each moment of correlation tells us that the underlying fabric is woven, continuous, holistic. And yet, because of decoherence, this holistic nature is concealed from daily life. We see the world in pieces because the environment constantly observes, constantly entangles, constantly breaks the quiet symmetries that exist at the smallest scales. But when isolation is achieved, in laboratories with careful shielding and exquisitely controlled conditions, the hidden harmony reappears. Entanglement revives. Superpositions grow stable. Quantum information flows in ways that classical reasoning cannot follow, and the underlying unity of the micro-world reveals itself once again. This unity is the foundation of quantum computing, of quantum encryption, of teleportation protocols that transfer states without moving particles. These technologies are not science fiction. They are demonstrations that the quantum world is as strange as it is fundamental. Entanglement, this quiet thread of shared existence, makes all of this possible. And so, as we drift toward the end of this section, one idea settles gently into place. The quantum world is not built from objects but from relationships, not from positions but from probabilities. not from isolated moments, but from woven states that tie pieces of the universe together in ways the classical mind was never designed to imagine. Let that understanding rest softly around you, a kind of gentle scaffold for the next idea. The next mystery, the next strange feature of the quantum realm. For in the next section, we explore how particles move through places they are not allowed to be, how they slip through forbidden regions, how they appear beyond barriers that classical physics insists are impenetrable, a phenomenon quiet, surprising, and utterly quantum. And when you're ready, we will step calmly into tunneling. There is a moment when two particles become linked in a way that no classical picture can fully explain. They may be created together, or interact briefly, or exchange a tiny packet of quantum information through some subtle process. After this interaction, their states are no longer separate. They do not carry individual descriptions that can be written down independently. Instead, they share a single wave function, not two wave functions sitting side by side, but one spread across both particles, as if the universe has drawn a quiet thread between distant points in space. Entanglement begins there. In classical physics, if you have two objects, you can describe each one completely without mentioning the other. Their states may influence each other, but they remain fundamentally independent. Quantum mechanics does not always allow this. It tells us that the complete description of the system may require both particles at once. There is no way to talk about one of them without referencing the other. This is why Einstein called it spooky action at a distance, even though no action actually travels between them. The spookiness is simply the strangeness of shared information in a universe built from probability waves. Imagine two electrons prepared in a state where their spins must be opposite, not because one is truly up and the other is truly down, but because the mathematical structure of their joint wave function requires opposite results when measured. Before measurement, neither electron has a definite spin direction. Each one exists in a superposition of possibilities, a cloud of potential outcomes waiting to be resolved, but the relationship between them is precise, perfectly correlated. If one is measured and found to be up, the other must be down. If one is down, the other must be up. These correlations are stronger than anything classical physics can create. Bell's inequalities were designed to test this. They attempt to quantify how strong correlations can be if particles merely share hidden instructions from the moment they separate. Instructions like, if asked this question, answer yes. If asked that question, answer no. Simple, local, pre-programmed rules. Quantum mechanics predicts correlations that go beyond what any such local instruction set can produce. And when experiments were performed, again and again, with different detectors, different timing systems, different methods, and extraordinary precision, the quantum prediction was confirmed. The correlations violate Bell's inequalities. They cannot be explained by classical hidden rules. The universe behaves as if the outcome of one measurement knows about the outcome of the other, even when the particles are separated by great distances with no time for any signal to travel between them. Yet nothing travels faster than light. No information is sent. No message is carried. The particles are not communicating. They are not sending signals or coordinating behind the scenes. They are simply two pieces of one shared quantum state, a state that spans space itself in a way our intuition struggles to visualize. When you measure one particle, you do not change the other. You simply reveal which branch of the shared wave function the universe is now occupying. The mystery is not about messages, but about reality itself being structured in a deeply connected way beneath the surface of space. Entanglement shows us that separateness is not a fundamental feature of the microscopic world. Distance becomes less meaningful, space becomes less of a barrier, and correlation takes on a new role as a form of unity woven into the universe's foundation. The beauty of this lies not in paradox but in coherence. Even when particles drift apart, even when galaxies lie between them, the mathematical structure that joins them remains intact until interactions with the environment break it down. Entanglement is fragile, easily disrupted. A whisper of environmental noise can destroy it. A slight disturbance, a faint electromagnetic nudge, even a distant photon brushing against the system, can cause decoherence and shatter the delicate link. But while it lasts, entanglement is powerful. It allows quantum computers to explore enormous spaces of possibilities all at once. It allows quantum teleportation of states from one region to another, using shared entangled pairs as the underlying resource. It shapes the structure of matter, governs the behavior of electrons in atoms, binds together the properties of materials, and may even be tied to the fabric of spacetime itself in some speculative theories. Some physicists imagine that entanglement patterns are the true scaffolding of reality, and that space emerges from these patterns like a smooth surface emerges from the positions of countless molecules. But even without entering those frontiers, the core idea remains calmingly clear. Quantum mechanics tells us that the world is connected in ways we cannot fully see, and that information is not always local. There is a softness in this realization, a sense that the universe is less like a collection of isolated objects and more like a single system whose parts move within a shared mathematical breath. As you drift through these thoughts, let the idea settle like a gentle wave. Two particles can share a single description, a single state, a single unfolding of probability, even when space lies between them. Entanglement is not a violation of physics. It is not a communication channel. It is not a loophole in nature's speed limit. It is simply a feature of a world written in the language of wave functions, where relationships are often more fundamental than positions, and where the deepest connections are invisible unless you know how to look. Imagine a barrier, a simple wall of energy or potential or structure, the kind of wall that, in the classical world, would be absolute. If a person walks toward a solid wall, they stop. If a ball rolls toward a ramp that is too high, it rolls back. If a planet orbits a star, it does not spontaneously jump to a different orbit or fall through the star or appear on the opposite side of the system without crossing the space between. In the world you know, motion follows clear pathways and obstacles block those pathways with certainty. But in the quantum world, certainty itself dissolves. And a barrier is never simply a barrier. Instead, a barrier is a region where possibilities grow thin, yet never fully disappear. At the smallest scales, existence does not behave like a collection of tiny marbles bouncing and colliding and remaining on the side where they began. It behaves like a wave of probability, a spread of potential, a distribution that cannot be confined perfectly to one side of anything. Every quantum object, an electron, a proton, a neutron, a molecule, even, under the right conditions, clusters of atoms exists not as a single point, but as a probability cloud, a wave function, a structure that extends. And because it extends, it presses against barriers and seeps into them and continues beyond them, even when classical logic would forbid such motion. This is the heart of tunneling, a quiet rule of the small where particles appear on the far side of a barrier without ever having enough energy to cross it in the classical sense. It is not a cheat or a violation or a glitch. It is a consequence of what it means to exist as a wave. When a wave meets a barrier, part of it reflects and part of it fades inside the barrier, and part of it, the tiniest, most fragile portion, continues through. Classically, if the energy is lower than the barrier, the particle would bounce back every time. Quantum mechanically, there is always a non-zero chance that the particle will be found on the other side. The wave function does not stop at the wall. It thins, it stretches, it decays exponentially, but it does not end. And wherever the wave function has a non-zero value, there is a non-zero chance that the particle will appear there when a measurement is made. This is why tunneling is not an exception to the rules of nature. It is the rule once you enter the domain where possibility replaces certainty, and where the boundaries of objects are not sharp but smeared across space. Imagine an electron trapped in a small region surrounded by potential walls, as if it were inside a quantum box. Classically, it should never escape. Its energy is too low, its kinetic motion too weak, its trajectory too tightly confined. But the quantum description does not see a rigid boundary. It sees a narrowing of possible states. The electron's wave function presses gently, invisibly against the walls of the trap, and though most of the wave is confined, its edges extend. On the far side of the wall, the wave function is faint but present, and with enough time, the electron can appear outside the trap, not by breaking through, not by digging, not by forcing its way, but by following the spread of its own probability. This process is quiet, effortless, governed not by force but by the geometry of possibility. Even a barrier that seems impenetrable invites a whisper of the wave through it. This is why tunneling is so deeply tied to the probabilistic skeleton of the quantum world. Nothing about it disobeys the laws of physics. Instead, it reveals the laws you cannot see in the macroscopic world, because their effects are too small, too subtle, too rapid, and too fragile to survive the noise of everyday life. In stars, tunneling is not small or rare or subtle. It is the engine. For two atomic nuclei to merge, they must come close enough for the strong nuclear force to overcome the repulsion of their positive charges. Classically, this requires enormous energy, much higher than the typical energy of particles inside a star's core. The sun, at its temperature, does not give most protons enough energy to collide and fuse. Classically, fusion should barely happen. Yet stars shine. They shine because protons tunnel. When two protons approach, their wave functions overlap, and even though their classical kinetic energy is too low, there is a finite probability that the combined system will tunnel through the electrostatic barrier and reach the region where the strong force can bind them together. Every second, countless such tunneling events occur quietly deep inside stellar cores. And every photon that warms your skin, every beam of starlight that crosses the universe begins with a tunneling event. Fusion, the engine of stars, would be nearly impossible without quantum tunneling. It is one of the quiet truths that the large depends on the small in ways you would never guess. Even life on Earth depends on tunneling. Inside the molecules of your body, electrons tunnel between atoms, forming and breaking bonds, allowing chemical reactions to proceed that would otherwise be too slow or too improbable to sustain biology. In electronic devices, tunneling is not just important, it is foundational. Modern transistors, the building blocks of computers, operate at scales where tunneling becomes significant. Electrons can tunnel through insulating layers, leak between regions, and shape the behavior of the circuits. Some devices, like tunnel diodes, use the effect deliberately to create unique electrical characteristics. The fact that you can listen to music, read text, or explore knowledge digitally often depends on electrons slipping through forbidden barriers in the quiet interior of semiconductor materials. The quantum world, always participating, always supporting the macroscopic one, even when unnoticed. And yet, for all its power, tunneling is gentle. It does not require breaking a barrier or smashing through it or violating conservation laws. The particle never gains extra energy, never cheats the system. It simply follows its wave function with perfect obedience. The strange part, the part that defies intuition, is not the mechanism, but the perspective. In the classical view, a particle is a point. In the quantum view, a particle is a spread. That spread allows it to occupy regions that would be unreachable if it were truly a point. And so tunneling is not motion but presence, not a journey but a probability, not a path but a distribution that extends beyond barriers and sometimes places the particle where classical reasoning says it should never be. Imagine standing before a mountain and knowing you cannot climb it. Then imagine that part of you, a faint part, a mathematical shadow, exists on the other side, quietly waiting, not because you crossed, but because you were never perfectly confined to begin with. That is quantum tunneling, a reminder that the small follows rules woven from possibility, not certainty, and that even the strongest walls are not absolute when existence itself is a wave. To understand tunneling more deeply, it helps to imagine the wave function itself as a kind of landscape. A landscape not made of hills and valleys, but of amplitudes and phases where the height of the landscape represents the likelihood of finding a particle in a certain place. In the classical world, a particle lives at a single point with a single position and a single path. But in the quantum world, the wave function spreads this possibility outward, giving the particle a softness, a presence, a reach beyond its center. When this landscape presses against a barrier, the part of it that lies inside the barrier decays sharply, but never immediately drops to zero. It simply becomes thinner, quieter, more fragile. The mathematics describes this decay as an exponential fall-off. The wave does not vanish at the wall, it leaks in. And when the wall is thin enough or low enough, or simply exists long enough, the wave that survives on the far side can be enough to give the particle a home there, a new possibility, a non-zero chance to appear. This is why quantum tunneling depends on the width of the barrier and not only its height. A tall barrier that is very thin might let the wave seep through more easily than a lower barrier that is extremely wide. The classical mind sees the barrier itself and judges its height. The quantum world sees the barrier as a region where the wave function shrinks but persists. The classical mind says blocked. The quantum world says unlikely but possible. That single phrase, unlikely but possible, is the foundation of quantum tunneling. And in a universe built on probabilities, possibility is not a luxury, it is the rule. Imagine now a scanning tunneling microscope, a device that can see atoms not by touching them, but by listening to the tunneling electrons between a sharp metallic tip and a surface. When the tip is brought close, electrons can tunnel across the tiny gap, forming a current that depends sensitively on the distance. Move the tip a little closer, and the current rises. Move it a little farther, and the current fades. By scanning the tip across the surface and measuring how the tunneling current changes, scientists can map individual atoms as if they were hills and valleys on a quantum landscape. You are listening to a universe that is not empty or rigid or simple. It is alive with constant shimmers of probability dancing even where nothing classical can move. Tunneling exposes that shimmer by allowing the wave function to briefly reveal its reach. Electrons become ghosts passing through narrow forbidden spaces, not because the barrier weakens, but because existence at this scale never truly stops at the boundaries that our intuition expects. Inside stars, tunneling is relentless. Protons vibrate, collide, and drift in the immense pressure of stellar cores. But their classical kinetic energy remains too low to overcome their electric repulsion. Without tunneling, fusion rates would be so small that stars might never ignite. But because quantum rules allow possibilities even when classical rules forbid them, protons merge, forming deuterium, then helium, then heavier elements in cycles that power the universe. Every atom in your body that came from a star, every carbon nucleus, every oxygen nucleus, every iron atom in your blood exists because tunneling allowed fusion to occur inside ancient suns. Without tunneling, the universe would be dark and cold and lifeless. The stars would simply never shine. This is one of the quiet truths of quantum mechanics. A phenomenon that seems small, almost ghost-like, almost negligible, supports the scale of galaxies and the evolution of worlds. The large rests on the strange softness of the small. Now consider radioactive decay. In certain unstable atomic nuclei, a particle inside the nucleus is trapped by a potential barrier formed by the strong nuclear force and the electromagnetic repulsion. Classically, the particle would remain trapped forever, its energy too low to escape the binding forces. But quantum mechanically, its wave function extends slightly outside the nucleus, just enough for there to be a finite chance that the particle will appear outside rather than inside. This appearance is interpreted as decay. A nucleus that seems stable for ages can suddenly emit a particle because its wave function finally placed that particle on the outside of a barrier. And so radioactivity, another phenomenon that shapes stars, planets, and biological evolution, is another manifestation of tunneling. The quiet departure of a particle from a region it never had enough energy to leave. Even in your own body, tunneling dances constantly. In photosynthesis, electrons tunnel along chains to convert sunlight into chemical energy. In smell, some theories suggest that tunneling may allow electrons to hop between molecules, helping the brain distinguish scents by their vibrational patterns. And in superconductors, electrons pair up and move through materials without resistance, in part because they can tunnel coherently through the entire structure. The world around you is filled with tunneling's signature, though you do not see the process, only its results. There is a softness at the heart of the small, a lack of rigid confinement, a willingness for the world to explore forbidden paths in quiet probabilities. And that softness is what gives matter the ability to form, react, transform, and shine. When an electron tunnels, it is not breaking rules. It is following the deeper structure of the quantum world. It is obeying the mathematics of waves instead of the intuition of points. It is respecting the way probability distributions behave when they meet boundaries. They do not stop abruptly, they fade. And wherever they do not vanish, the universe can place the particle when asked. The classical world sees barriers and assumes they are absolute. The quantum world sees barriers and whispers, "Let me check." Sometimes the answer is no. The particle remains confined and nothing changes. But sometimes quietly, rarely, yet inevitably, the answer is yes. A presence is found on the far side of a wall even though no motion in the classical sense ever occurred, and that quiet yes fuels stars, drives evolution, enables chemistry, powers electronics, and shapes the structure of reality. Tunneling is often described as a particle passing through a wall, but the deeper truth is that there is no tiny bead moving along a single trajectory and then slipping through a gap. Instead, there is a wave function spread across space, a quiet cloud of possibility that extends farther than intuition expects, and that cloud never fully ends, even where classical energy runs out. The barrier does not crush it or silence it. It only dims it, softens it, thins it. And where the wave function still has amplitude, the particle still has presence. This is the central idea behind all tunneling. A particle appears on the far side of a barrier not because it shattered the wall, but because its wave never fully stopped at the wall to begin with. When you hear this idea, it may sound poetic, but it is not. It is written directly into the mathematics of quantum mechanics. A decaying exponential, a solution to Schrödinger's equation. A wave that fades but does not vanish. The math itself promises the possibility. Now imagine a single proton in the core of a star, shaking, vibrating, colliding with others in an ocean of unimaginable density. Protons repel each other because each carries a positive charge. Classically, this repulsion forms a towering barrier, too high for the proton to climb with the thermal energy available. But quantum mechanics offers another route. The wave function of the proton presses into the barrier and fades, and beyond that fade it still exists as a faint possibility. This faintness is all that fusion needs. The proton's wave function on the far side of the barrier is enough to permit the merging, the sudden union with another proton through the strong nuclear force. And once that union happens, a chain of reactions can begin. Reactions that generate light, heat, and the heavy elements that fill your world. Iron in your blood, oxygen in your breath, carbon in your cells. All of it exists because tunneling allows stars to burn. The warmth of the sun, the glow of starlight, the chemistry of life, the evolution of planets, and the shape of galaxies, all trace their origin to this quiet quantum process in the hearts of ancient suns. Tunneling is the whisper that lets the universe shine. Consider now how tunneling operates in semiconductors. Inside computer chips, electrons move not like tiny balls rolling between tracks, but like waves interacting with potentials. Transistors, the tiny switches that form logic gates, depend on the ability of electrons to tunnel through insulating layers when conditions change. If the layers are too thin, electrons tunnel when they should not. If the layers are too thick, electrons cannot tunnel when they must. Modern engineering balances these thresholds with precision, measuring thickness in single nanometers. The quantum world sets the rules for digital logic, and every device you interact with daily, from phones to satellites to medical equipment, relies on this quiet, probabilistic motion inside crystals. Even superconductors operate under rules where electrons can tunnel as pairs across insulating barriers, creating what is called a Josephson junction. This tunneling allows superconducting circuits to oscillate with frequencies so stable that they are used as time standards and in quantum computing to create qubits that store the phase of a tunneling wave. Tunneling is not rare. It is not exotic. It is not an exception. It is a normal expression of quantum behavior that becomes visible whenever barriers are narrow and energies fluctuate gently. To picture it clearly, imagine a particle's wave function as a soft glow, spreading out across a region of space like dim light filtering through fog. When it meets a barrier, the glow begins to fade. But unless the barrier stretches to infinity, the glow always reaches through, even if only faintly. And where there is glow, there is possibility. And where there is possibility, outcomes can occur. This is why you can never predict exactly when a radioactive particle will be emitted. Its appearance is governed not by a countdown, but by probability, a constant likelihood per unit time that the particle will be found on the far side of the barrier. This is what gives rise to the concept of half-lives, a statistical measure of how long it takes for half the nuclei in a sample to tunnel outward. The nucleus is not sitting there deciding when to decay. It is simply evolving under the quiet rules of the quantum world, and the barriers around it allow escape only through the shape of its wave function. Tunneling reveals a deeper message hidden in the mathematics. Boundaries are not absolute. Walls are not perfect. Confined systems are not fully confined. In the world of the small edges are gradients, and confinement is a matter of probability, not certainty. And so the quantum world is not a world of rigid separation, but of permeable boundaries. Electrons dance between energy levels in atoms by tunneling. Photons escape from quantum wells in LED materials through tunneling. Molecular reactions occur because particles can tunnel between configurations that classical chemistry would never allow. Even the folding of proteins and the behavior of enzymes may involve tunneling as atoms shift in ways too subtle for classical mechanics alone to explain. Everywhere you look beneath the surface of classical intuition, tunneling whispers. Paths exist, even when they seem forbidden. The universe is not rigidly locked into single trajectories. It explores many quiet possibilities and sometimes chooses outcomes far beyond what classical logic would predict. And because of that, stars ignite, life evolves, electronics function, and the universe remains a place of continuous transformation. With this, all the ideas of Section 5 have now been fully explored. Whenever you're ready, we will move gently into Section 6, the quantum field view of the universe, where the very idea of particles gives way to something even more fundamental. At the smallest scales, the universe does not begin with particles, it begins with fields, invisible, continuous everywhere, spread through space like a quiet fabric that you cannot touch but that touches everything. A particle is not a tiny bead moving through emptiness. It is a vibration, a localized ripple inside one of these fields. This is the framework known as quantum field theory, a deeper layer beneath the image of particles as discrete little objects. Every type of particle is linked to a specific field: the electron field, the photon field, the quark fields, the neutrino fields, not separate in location but separate in identity, all of them filling space entirely. Even the most silent vacuum is not empty. It is saturated with these fields resting in their lowest energy state, waiting to be stirred. A field is like a calm ocean, and a particle is like a single wave rising for a moment before falling back into stillness. This idea is not metaphorical. In the mathematics, there is nothing truly like a dot or a bead or a point-like speck. There are only excitations and patterns and disturbances propagating through a continuum. The photon, the carrier of light, is simply a vibration of the electromagnetic field. The electron is a ripple in the electron field. A quark is a trembling mode of the quark field. And all forces, all interactions, all structures emerge from the way these ripples interfere, merge, and exchange energy. When you see a beam of light, you are not watching countless little pellets flying through space. You are watching the electromagnetic field choosing for a brief moment to vibrate. When you touch the surface of your desk, you are not touching tiny spheres of matter. You are feeling the interplay of electron fields repelling each other, their excitations overlapping and producing resistance. Even the solidity of everyday objects is a field phenomenon, a quiet choreography of quantum oscillations holding form in a sea of motion. In this view, vacuum itself is alive with structure. Not structure you can see or detect directly, but structure written into the energy behavior of the fields themselves. The vacuum is the lowest energy state. Not a true nothing, but a subtle hum of fluctuations never fully still. Virtual particles are not little objects popping in and out of being. They are momentary ripples allowed by uncertainty, brief, ephemeral, but real enough to influence forces and the behavior of fields. When two particles interact, they are not colliding as classical intuition imagines. Their fields overlap and interfere, and the mathematics of this interference predicts the outcome. Every interaction, every exchange of energy is a communication between fields, a whisper transmitted through the quiet structure beneath reality. Some fields are simple. The electromagnetic field vibrates cleanly with a clarity that allows light to spread almost effortlessly. Other fields are more complex. The quark and gluon fields form the restless interior of protons and neutrons. Their interactions are so strong that quarks become confined, never able to escape each other's influence. This confinement is also a field effect. a constant tension inside matter, a binding generated by the rules of the quantum fields that shape your world. Even mass itself is a field phenomenon. The Higgs field fills all of space like a subtle cosmic density. Particles interacting with it gain inertia. They resist acceleration because the Higgs field gently tugs against change, and this resistance is what you call mass. A proton has mass because of the energy of its internal quark fields. An electron has mass because the Higgs field slows its motion. Photons having no interaction with the Higgs field remain massless forever, racing at light speed. Everything you experience as weight, inertia, solidity, and matter, all of it emerges from the dynamics of fields. Even space itself may not be a backdrop, but a participant. Some physicists suspect that space-time could itself be a field-like structure capable of curvature and oscillation. Gravity waves rippling across the cosmos are vibrations of that structure. And so the world you move through is not built from little marbles of matter. It is woven from continuous underlying fields. Each one overlapping each one, interacting each one, influencing the others in a delicate mathematical dance. This picture may feel abstract, but in the quiet of late night it reveals something soothing, that beneath the noise and motion and complexity of everyday life, there is a deeper foundation, calm, continuous, ever-present, a framework that does not rush or scatter, a framework that simply is. The quantum fields never sleep. They ripple and settle and ripple again, maintaining the fabric of everything you have ever known. Even when no particles are present, even when silence fills the room, even when the universe seems still, the fields remain, quietly vibrating beneath existence. The idea that everything you have ever touched or seen or thought about is ultimately a vibration in underlying fields may seem abstract, but it explains why particles are identical. Every electron anywhere in the universe is not a separate object that happens to look the same. It is the same excitation of the same field, a specific pattern that the field produces whenever conditions allow it. You cannot tell one electron from another, not because they merely look the same, but because they are literally the same mode of the same field. An electron in your body and an electron in a distant star are expressions of one continuous entity, the electron field woven throughout the cosmos. The same is true for photons. Each photon is a ripple of the same electromagnetic field. No individuality, no personal identity, just a pattern rising and falling in the same ocean. This is why physics has such remarkable precision, why equations predict results to unfathomable accuracy. Because nature is not dealing with millions of unique objects, it is dealing with single fields following single sets of mathematical rules, repeating themselves perfectly everywhere. Even the forces between particles emerge from interactions between fields. When two electrons repel, it is not because they sense each other as tiny charged beads. It is because disturbances in the electron field interact through the electromagnetic field, one field affecting another in a structured, predictable way. The force is the field response, not a physical push, but a shift in the energy configuration of the fields themselves. When a proton attracts an electron to form a hydrogen atom, the fields settle into a stable configuration, a quiet arrangement that minimizes energy. The atom is not a thing, it is a pattern, a stable knot in the tapestry of interacting fields. Even chemical bonds are field configurations, shared electrons residing in overlapping regions of the electron field, creating shapes that form the geometry of molecules, not by mechanical connection, but by the quiet rules of quantum fields seeking low-energy harmony. Everything complex, everything alive, everything textured and tangible is a structure emerging from this deeper level. The fields do not care whether they form a star or a leaf or the water in your veins. They follow the same rules, vibrating, interacting, seeking stability or motion or decay, depending only on the landscape of energy. When a particle decays, what is happening is not the disappearance of a little object. It is a rearrangement in the fields. One excitation relaxing into another, energy dispersing from one pattern into new patterns. All through the dynamics written into the equations of the fields. Even pair creation and annihilation are field processes. A photon with enough energy can create an electron and a positron, not from nothing, but because the field system permits a transition from one vibration into two new ones, as long as the energy and quantum numbers are balanced. The vacuum is the foundation for these transitions, a baseline energy not empty but poised. Like a tightly coiled spring that occasionally releases or absorbs tiny fluctuations. The vacuum is full of potential, a sea whose surface is never perfectly calm. Every physical event happens against this background, even if you are unaware of the restless motion beneath. The fields are always present. Your body is a dense collection of excitations, but even outside your skin and the quiet air around you, the fields extend, continuous, smooth, unbroken. You are immersed in them constantly, living inside a medium you cannot detect directly, yet depending on it absolutely for every sensation and breath. There is no edge to the electron field, no boundary to the photon field, no corner of the universe where the quark fields simply stop. If you were drifting alone in deep space, far from any star, the fields would still be there filling the void, quiet but present, calm but ready to ripple if disturbed. This is the hidden structure beneath reality, a structure more fundamental than atoms or particles or molecules. It is the level where nature speaks its most basic language, not in objects but in vibrations, not in things but in patterns, not in matter but in fields. And underneath the complexity of the equations, there is a strange, gentle simplicity. Everything is excitation. Everything is interaction. Everything is vibration in a quiet, ever-present foundation. The classical world, the world you move through, the world of chairs and planets and warm hands, floats on these fields, held together by their dynamics, stabilized by their interactions, shaped by their rules. Even though you cannot see them, even though they move too fast and too subtly to be sensed, they are the reason anything exists at all. And yet, for all this coherence, for all this quiet unity, there is still an element of unpredictability. Because at the smallest scales, the fields do not settle into perfect stillness. They vibrate with tiny fluctuations even when no particles are present. These fluctuations are not noise from the outside world. They are built into the mathematics of the fields themselves, a consequence of the uncertainty principle woven directly into the fabric of quantum reality. Even the vacuum cannot be completely calm. There is always a minimum amount of jittering energy, a restless baseline from which nothing can fully escape. This vacuum activity is why empty space is not truly empty, why pairs of virtual particles can appear and vanish in impossibly short times, not long enough to be directly observed, but long enough to affect the behavior of real particles. A lone electron moving through space is never quite alone. It is surrounded by a constantly fluctuating cloud created by the vacuum fields, a shifting sea that slightly alters its mass, its charge, its behavior. These corrections are essential to making the theory match experiments, and they reveal that fields are not superficial constructs. They are the deep machinery from which everything emerges. Even light moves through this restless sea, not slowed but subtly influenced. Its path can be bent by the presence of other fields. Bent by gravity, which itself may be understood as a curvature in a deeper field-like structure, a geometry that shapes how all other fields evolve. Every interaction is ultimately one field responding to another. When two particles scatter, they are not colliding like billiard balls. They are exchanging momentum through field couplings, one field transmitting energy to another through virtual excitations that flicker and vanish. The mathematics describes these interactions with exquisite precision, Feynman diagrams mapping out how fields influence each other. Each line, each vertex, a symbolic guide to the underlying process. Not a literal picture, but a reminder that particles are not little objects traveling along lines. They are disturbances propagating through fields, changing shape, interacting, merging, splitting, as the fields themselves obey the rules set by their symmetries. Symmetry is one of the deepest ideas in quantum fields, a hidden order that dictates what interactions are possible and which ones are forbidden. If a symmetry forbids it, nature will not allow it, no matter how much energy you provide, no matter how many chances you give it. Symmetry creates conservation laws, conservation of charge, conservation of spin, conservation of energy. All arise because the fields possess certain invariances, ways they can be shifted or rotated without changing the physical situation. These symmetries are like the deep grammar of the universe, rules so fundamental that nothing can break them. They shape the interactions, the particles, the forces, all from properties that exist in the equations beneath everything else. The photon field has a symmetry that guarantees the conservation of charge. The electron field has a symmetry that gives rise to the electron's spin. Every property, every rule, every force is linked to these underlying principles. Even mass can be understood as a field interaction, not an inherent property, but a consequence of how the particle fields interact with deeper fields, like the Higgs field. A field that permeates space quietly uniformly, its presence providing a kind of drag that makes some particles resist acceleration, giving them mass, while others like the photon slip through effortlessly, remaining massless, moving at the speed of light. If the Higgs field vanished tomorrow, all matter would behave differently. Electrons would fly apart, atoms would collapse, the world would dissolve into a bath of unbound energy, not because objects were destroyed, but because the fields that shaped them lost one of their connections, one of their constraints. Everything stable about the universe arises from these fields, and every instability, every transition, every reaction is also an expression of their dynamics. When you heat matter, you are increasing the energy of its field excitations. When you cool it, you guide those excitations into lower configurations. When something melts or freezes or evaporates, it is not just molecules moving, it is the field system shifting into a new pattern, a new balance of excitations and interactions. Even superconductivity, the ability of materials to conduct electricity without resistance, is a feature of field behavior. Electron pairs moving coherently through the lattice, guided by field interactions that suppress scattering. And inside the heart of stars, tunneling fusion radiation, all of them are field processes, shaped by the rules of quantum interactions, not by classical collisions. You live in a universe where everything is made of fields, fields that cannot be separated from one another, fields that fill space and time, fields that form the quiet foundation beneath every object, every atom, every breath. And the more deeply you follow this idea, the more gently it shifts your sense of reality. Matter becomes pattern, particles become vibrations, vacuum becomes a sea of potential. And existence becomes a tapestry of interacting waves, filling the universe without gaps or seams, a continuous silent structure beneath everything. The more you follow this idea of fields as the true substance of reality, the more classical images begin to dissolve. The solid shapes you are used to imagining fade into patterns, patterns of amplitude and phase, patterns that change when other fields move through them, patterns that propagate through space like quiet ripples in a vast, invisible ocean. A particle is just a stable ripple, a configuration that maintains its identity while traveling from one place to another, but the underlying medium is the field, always present, always extending, always capable of creating a disturbance at any point in space if given the right energy. This picture is so different from the old mechanical idea of tiny pieces of matter, yet it explains every experiment with astonishing precision. It explains why particles annihilate into pure energy. Because the ripples can cancel each other, leaving only the fields and their vibrating energy. It explains why new particles can appear from energetic collisions. Because the fields are always there waiting to be excited. Everything you think of as creation and destruction in particle physics is really just the rearrangement of excitation patterns. Ripples joining ripples, fading ripples transforming, the fields themselves remain continuous, immense, enduring everywhere. Even the vacuum is not a blank backdrop. It is a restless stage filled with possibility, its fluctuations altering the energy levels of atoms, shifting frequencies, influencing behavior. One of the most delicate examples is the Lamb shift, a tiny change in the spectral lines of hydrogen, so tiny that only with careful measurement could it be found, and yet it is a direct imprint of the vacuum fields at work, virtual particles appearing and vanishing too quickly to observe, but long enough to shift what the atom feels. This hidden motion is woven into everything, into the chemistry of molecules, the structure of atoms, the stability of the world. Fields decide how electrons arrange themselves around nuclei. They decide which configurations are stable, which ones will absorb energy, which ones will emit it. The entire periodic table and all its behaviors flow from the quantum fields and their symmetries. And inside stars, where pressures and temperatures reach extremes beyond anything familiar, Quantum field interactions control the processes that power them. Nuclear fusion occurs not because nuclei can overcome their natural repulsion, but because a tiny fraction can tunnel through the barrier. A behavior that only makes sense when you recognize that particles are waves, and waves can extend beyond obstacles. When those waves interact in the star's core, the fields respond, producing light, heat, and the elements that later form planets and life. So even the stars owe their brilliance to quantum fields, to the quiet mathematics that governs the smallest scales, a mathematics that unfolds into cosmic phenomena. When you look at the night sky, you see the result of countless field interactions. Photons that began as excitations in plasma, traveling for millions of years, through space that is full of its own fields. Until finally the light enters your eye, triggering excitations in the electric fields of your neurons. Everything is fields interacting with fields, from the birth of stars to the quiet spark in your visual cortex that lets you see them. And yet, despite this complexity, despite the layers of interacting ripples, the universe behaves with extraordinary consistency. The photon field is the same everywhere. The electron field is the same everywhere. Its properties do not drift from galaxy to galaxy. Its mass, its charge, its behavior are constant. This uniformity is one of the deepest mysteries. Why should the same fields extend unchanged across billions of light years? Why should their symmetries remain perfect from one end of the cosmos to the other? There is no clear answer, only the understanding that if the fields were not uniform, if their symmetries shifted in different regions, the universe would not look the way it does. Atoms might not hold together, chemical reactions might not proceed, stars might not burn, life might not be possible. So when you touch the world around you, when you breathe, when you hear your own thoughts, you are interacting with the quiet, stable fingerprints of quantum fields, fields that made possible every pattern of matter, every molecule in your body, every spark of consciousness. And beneath all these fields is still another layer, a deeper unity. Hints of it appear in our attempts to unify the forces. Electroweak unification showed that two forces, once thought separate, the electromagnetic and the weak, are simply different expressions of one field structure. Symmetry broken gently as the universe cooled. Perhaps the strong force and the electroweak force originate from a deeper symmetry still. Perhaps gravity emerges from the geometry of a more fundamental field. We don't yet know, but the search reveals something profound, that the deeper we look, the more unified the universe becomes, the more the pieces begin to blend, until everything might be expressions of a single set of rules, a single architecture beneath reality. Even now, physicists imagine fields that have never been seen, new gauge fields, new symmetries, new excitations. Some may exist at energies far beyond what we can reach. Others may subtly influence dark matter, or contribute to the vacuum energy, or whisper through cosmic evolution in ways we have not yet understood. Every theory that tries to describe the deepest layer, quantum gravity, string theory, loop approaches, all of them paint the universe as a network of interacting structures, vibrations, curvatures, fields, or something even more abstract, but always emerging behavior, always something beneath the surface shaping what we see. And even if the true foundation is deeper than what we call fields, quantum field theory remains the most accurate description ever created, predicting measurements to astonishing precision, a theory that nature seems to whisper through every time we look closely. The idea that everything is built from fields is both startling and calming, because it means that reality is not a collection of isolated pieces. It is continuous, interconnected, coherent, a single vast vibrating structure, in which you and stars and particles and empty space are all patterns woven from the same foundation. If there is a border between matter and energy, between emptiness and existence, it is a border made of mathematics, not of walls, a boundary drawn not by nature but by the limits of human imagination. As you drift deeper into this picture, the idea of a field becomes less like a physical substance and more like a rule that space must follow. A rule that tells every point how it may vibrate, how it may store energy, how it may interact with every other point. When physicists say that a particle exists somewhere, they mean that the excitation of a field has concentrated there. A ripple has formed, a ripple that can influence other ripples. A ripple that can travel, a ripple that carries information through space. The entire universe is nothing but the evolution of these excitations. The movement of patterns, the spreading of vibrations, the quiet interaction of fields across emptiness. And even emptiness is only the state of minimum activity, not zero activity. Never zero. Because even the lowest state of a quantum field is filled with fluctuations. A perfect stillness is impossible. There is always a hum, a whisper, a gentle trembling written into the mathematics. This hidden motion is responsible for astonishing phenomena. The Casimir effect, where two uncharged metal plates feel a force because the vacuum fluctuations between them are restricted. The energy outside the plates is ever so slightly different from the energy between them, creating a pressure from the vacuum itself. It is not magic, it is the fields expressing their nature. Fields cannot be silent. Silence is not part of their vocabulary. Even the cosmological constant, the energy density of empty space, may be connected to the restless structure of the quantum vacuum, though we do not yet understand why its value is so small, or why it exists at all. Everywhere you look, the vacuum is not a background, it is the true foundation, the stage on which every excitation moves. And the stage itself is active, alive, dynamic, quietly shaping the universe moment by moment. This picture also changes the way we think about identity. If particles are excitations of fields, then two electrons are not two separate objects. They are two manifestations of the same field, two ripples in the same ocean, two patterns in one continuous medium. This is why electrons are identical, exactly identical. They do not have individual personalities or subtle differences. They are simply excitations of a single field, and that field never changes its properties, no matter where you look. This is also why every proton has the same charge, every photon the same speed, every quark the same mass, because these properties belong to the fields, not to the excitations. It is a picture of deep unity, a universe where the individuality of particles is an illusion, where the true identity belongs to the fields, enduring, universal, shared across all space. Even the laws of physics arise from the symmetries of these fields: rotation symmetry, gauge symmetry, Lorentz symmetry, mathematical structures that determine what kinds of particles can exist, what forces can arise, what interactions are possible, and what interactions are forbidden. The universe is constrained by these symmetries, guided by these principles, and yet the result is a world with extraordinary variety. Stars, galaxies, molecules, life, all arising from a handful of simple field equations. The complexity of everything you see is the consequence of patterns stacking upon patterns, excitations combining, fields interacting, waves interfering, all governed by rules quietly carved into the fabric of existence. If you look at the cosmos through this lens, it becomes a continuous structure, not a collection of separate pieces, but a single interwoven entity, where every movement in one region alters the fields everywhere else. Even if the change is too small to detect, the fields feel it, because they are one. And if you zoom in to the smallest scales, all the way down to the Planck length, the fields themselves might begin to flicker in even stranger ways. Their smoothness might give way to something granular, something foamy, something shaped not by continuous waves, but by deeper quantum geometry. Hints of this appear in attempts to unite quantum field theory with gravity, but no one yet knows what the final picture will look like. Perhaps the fields will dissolve into strings, or networks, or loops, or something beyond imagination. Yet whatever the next layer is, it will need to preserve the astonishing accuracy of the fields we already know, because the predictions they produce match experiments to a precision that is almost surreal, like the magnetic moment of the electron, measured and calculated to more decimal places than almost any other number in science. A triumph that reveals how deeply quantum fields capture the structure of reality. So when you breathe, when you move your hand, when your thoughts flow quietly in the dark, quantum fields are responsible, firing neurons, generating potentials, driving the chemistry that sustains life. You are not separate from these fields. You are not built from objects. You are made of patterns, configurations, standing waves in a set of fields that fill the cosmos. You are connected to everything through these fields, because the fields are continuous, everywhere, unbroken. They do not stop at the boundary of your skin. They do not end where the air begins. They do not halt at the edge of space. They extend beyond galaxies, beyond clusters, across the entire observable universe. And when you look at the night sky, you are seeing the ripples of these fields, light arriving from distant fires, carried by the same photon field that vibrates in this room, the same field that vibrates in your nervous system, the same field that allows you to see, to think, to understand. The universe is one connected structure, a single vibrating body, and quantum field theory is the language that describes its deepest behavior. If you let yourself drift, you can almost feel the unity, the way every event is tied to every other, the way all motion is part of one continuous whole, a quiet cosmic harmony, soft, delicate, interlaced, extending everywhere. The world you move through each day feels solid, definite, clear, stable. Chairs stay where you place them, keys remain in your pocket, your hand does not drift into several positions at once. Yet the rules underneath these familiar experiences, the quantum rules, do not offer certainty or solidity or anything fixed. At the smallest scales, superposition is natural, probabilities flow and overlap, particles explore many paths at the same time, and the boundaries between states are soft, almost fluid. So the question rises gently, almost like a whisper drifting through a quiet room. If the foundations of the world are quantum, why doesn't the world you see behave that way? Why is everything so definite, so settled, so clear, when the building blocks are not? The answer belongs to a slow and subtle process, a process that washes quantum strangeness into classical certainty. As if the universe itself is constantly tidying the loose threads of possibility. This process is called decoherence, and it begins with something very simple, something almost invisible, yet endlessly powerful. It begins with the environment. Every object around you, every atom, every molecule is constantly interacting with countless others. A grain of dust colliding with air molecules, a warm surface exchanging infrared photons, a small vibration radiating into surrounding materials. All of this contact, all of this exchange, acts like a continuous measurement. Not a measurement by a human, not a measurement by an instrument, but a measurement by the world itself. Whenever something quantum interacts with its surroundings, its delicate superpositions leak into the environment, spreading out, diffusing, mixing with countless particles. The environment, without intention, without awareness, quietly absorbs the quantum information, and in doing so washes away the interference patterns that would otherwise allow an object to remain in many states at once. It is not destruction, not collapse in the dramatic sense, but a gentle dispersal, a smearing out of microscopic possibilities into a vast sea of interactions. Imagine a drop of ink falling into water. At first it is concentrated, distinct, separate. But the moment it touches the larger fluid, its structure dissolves, its identity spreads out, its boundaries fade. Quantum superpositions behave like that ink. When isolated, they hold their shape. But the moment they brush against the environment, the moment they are touched by countless interactions, their structure no longer remains intact. They dissolve, not into nothing, but into the fabric of the surroundings. And what remains behind is a single classical outcome, a position, a state, a definite value. A world that appears stable. Even a small object, something you could hold in your hand, contains trillions of quantum particles, all interacting constantly with each other and with the environment. The result is a deep and seamless loss of quantum coherence, so complete that no interference patterns survive on scales you can see. Only in extreme care, extreme isolation, and extreme cold can coherence be preserved. Scientists place fragile systems inside vacuum chambers, surround them with magnetic shields, cool them to near absolute zero, and still, the tiniest interaction can undo their quantum delicacy. A single stray photon, an unexpected vibration, a microscopic collision, that is how sensitive superposition is. In your everyday world, where air molecules collide billions of times each second, and objects are bathed in light, and temperature drives constant motion, superpositions cannot survive. They are continuously eroded by the gentle touch of the environment. And because of this, the classical world emerges, not because classical rules are fundamental, not because macroscopic objects have moved beyond quantum reality, but because decoherence hides quantum behavior behind endless interactions. You do not see a table in a superposition of positions, because every photon striking it, every molecule of air brushing its surface, every vibration passing through its structure is already measuring it, pinning it into one stable configuration. And so your eyes, your hands, your memories encounter a world that appears definite and reliable, even though, beneath the surface, the quantum rules still guide everything. The classical world is an illusion of scale, a gentle averaging out of endless microscopic probabilities, a simplification created by decoherence. Even your own body, your neurons, your thoughts exist within this blend. Quantum rules underneath, classical stability above, layered together like waves beneath a calm surface. And yet, if you look closely, if you gaze far enough into the small, you can still see the shimmer of that deeper structure. Electrons tunneling through biological molecules, photons maintaining coherence in delicate pathways, atoms in your cells vibrating with quiet quantum fluctuations. The world you touch is classical in appearance, but quantum in truth, a soft merging, a gentle transition, from the mysterious to the familiar, a bridge built by decoherence, carried by every interaction, woven into every moment. In the next continuation, we will drift deeper into this boundary, exploring how classical certainty takes shape and why macroscopic objects cannot explore many states at once. And we will let the edges between quantum and classical soften even more as we continue to rest in the strange beauty of the small. Even now, as you rest, the boundary between quantum possibility and classical certainty is unfolding everywhere around you. Not with drama, not with sharp transitions, but with an unbroken sequence of tiny interactions. Each one so small it would escape any instrument, yet together they build the familiar world. A world in which objects do not shimmer between positions, do not split into many paths, do not echo with overlapping futures. The moment a system touches its surroundings, even in the faintest way, its quantum phases begin to disperse. They spread outward, like ripples merging into countless others, like a whisper dissolving into wind. The information that once defined the superposition is carried away, encoded into vibrations, into scattered photons, into subtle shifts in air and matter. The world, without intention, absorbs the quantum story. And when that story is spread wide enough, so wide that no observer could reconstruct its coherence, the system appears classical, a single outcome, chosen by the quiet blending of infinite tiny influences. This is why the large cannot behave like the small. An electron can hold a delicate superposition because it is almost weightless, almost isolated, almost untouched. But a chair or a cup or a human hand is made of countless atoms interacting constantly with the environment. Temperature shakes them. Light hits them. Air molecules bounce against them. The very structure of a macroscopic object is flooded with interactions. Too many interactions for quantum phases to remain intact, so the superpositions disappear almost instantly, long before you could ever notice them. In this way, classical reality is not a separate world or a separate rulebook. It is simply the quantum world blurred by endless contact, by the touch of air, of thermal motion, of light, of the environment itself. You never see a car in two places at once, not because it cannot be, but because the information that would allow it is erased faster than any possible detection. Quantum behavior requires protection, stillness, isolation from the outside. The universe never provides that for large objects. Only in rare laboratories, under deep vacuum, extreme cooling, and careful shielding, can coherence survive long enough for scientists to detect macroscopic quantum states. Even then, they are fragile. A single stray interaction, a microscopic vibration, a single photon can collapse the experiment. This fragility is why your world is stable, why your memories are consistent, why your surroundings stay familiar, why you can rely on continuity. Decoherence builds a world of clarity, not by changing the quantum laws, but by smoothing them, averaging them, washing away the hidden possibilities that small systems can hold. And yet, underneath that classical calm, the quantum rules remain, always present, always active, always shaping reality. Even though you do not see it, every atom in your body obeys these rules. Every electron in your neurons, every photon absorbed by your eyes, every vibration of a molecule, all of them follow quantum principles, hidden beneath layers of decoherence. The classical world is a useful simplification, a picture painted from the blending of interactions, a surface view of something deeper. If you could lift that surface, if you could silence the noise of the environment, you would see the world shimmer with possibilities. Superpositions unfolding, interference weaving patterns, entanglement stretching across space, all of it still there, quiet, subtle, foundational. This dual nature is one of the most striking truths of modern physics. The world is quantum, through and through, but what you experience is a softened version, filtered through decoherence. Like a storm seen through frosted glass, its details blurred, its edges smoothed, its motion reduced to gentle, uniform shapes. Classical reality is that frosted layer, a protective cloak, formed by interaction, covering the unpredictability beneath. But the unpredictability remains. A leaf does not fall in exactly the same way each time. A flame flickers with subtle variations. A molecule vibrates with patterns no classical equation can ever fully predict. Even at human scales, traces of quantum randomness leave a signature, soft, faint, but present. A reminder that the classical world is not rigid, not perfect, not absolute. It is an emergent harmony, sustained by decoherence, a balance between the chaotic possibility of the quantum and the orderly structure you rely on each day. And in this balance, there is a quiet beauty, a sense that the universe does not require sharp divisions or rigid boundaries, only gradual transitions, smooth gradients, and gentle blending. The quantum supporting the classical hiding the quantum, two descriptions of one reality. The classical world feels stable because decoherence never stops. Every moment, every interaction, every touch of the environment reinforces a single outcome. The universe behaves like a vast, silent observer, not choosing a result, but washing away every fragile alternative. When a particle interacts with its surroundings, the quantum phases that encode its possibilities spread outward into countless degrees of freedom. They disperse into air molecules, into thermal vibrations, into photons bouncing around the room. Information becomes diluted, smeared so thin that no detector could ever gather it again. The superposition still exists in the full mathematical description, but for all practical purposes, it has dissolved. Its delicate structure faded into environment-sized noise. And this is why the world you experience feels sharp, solid, and definite. Not because the quantum rules stop operating, but because their subtleties are drowned in the ocean of interactions surrounding every macroscopic object. Think of a violin string, vibrating alone in a quiet room. Its tone is pure, its frequency clear. But imagine playing that same note in the middle of a roaring crowd. Layered sounds, endless vibrations, interference from every side. The purity vanishes, even though the string is still vibrating. Quantum coherence is that pure tone, and the classical world is the overwhelming noise that absorbs it. The moment a system touches the world, its quantum harmony is scattered outward, and what remains is the appearance of a single defined state, a classical result, not chosen, not enforced, simply left over after the delicate structure of superposition has been smoothed away. The emergence of classicality is therefore an emergent phenomenon, a property that arises not from new laws, but from the overwhelming accumulation of interactions, from the fact that every object is a system of many parts, each one constantly in motion, constantly exchanging energy, constantly entangling with its surroundings. A chair, a cup, a stone cannot maintain quantum coherence because every atom inside them is already connected to countless others. Each vibration, each collision, each photon, absorbed or emitted, acts as a tiny measurement. And these tiny measurements occur billions of times every second. Too many for superposition to survive. So the large becomes classical, predictable enough for stability, unpredictable enough for life. A balance that lets the universe be both structured and creative. This balance is not separate from the quantum world. It is built on it. Under every classical surface lies a quantum foundation, a world of fields, of fluctuations, of non-local correlations, of amplitudes and interference, all hidden beneath the constant wash of decoherence. Every table, every planet, every galaxy, every cell in your body is held together by quantum rules. But what you see, what you feel, what you navigate through is the stabilized version, the version where quantum possibilities have been averaged out, blurred into definite outcomes. The classical world is the quantum world after the universe has taken a long, gentle average. Even your thoughts, your memories, your waking consciousness emerge from processes that would be impossible without decoherence. Neurons fire in patterns that require classical stability. And yet each neuron relies on quantum processes inside ion channels, inside proteins, inside the atomic structure that makes biology possible. Your mind is a classical phenomenon built on a quantum foundation, a fusion of order and underlying uncertainty. And this fusion is only possible because decoherence gives the macroscopic world its shape. Without decoherence, identity would not persist, objects would not hold form, memories would not be reliable. The classical world is the universe's way of creating continuity, a continuity woven from countless dissolving superpositions. It is not that quantum rules change, they never do. It is that interactions hide their more delicate patterns, smoothing them into stability. So when you look at the world, what you see is the average tapestry, but the threads underneath are quantum, always flickering, always fluctuating, always exploring possibilities. Decoherence simply blurs that hidden complexity into the familiar picture your senses understand, a picture of objects with positions, paths with certainty, moments with definite outcomes. Even though the universe does not fundamentally operate in those terms, classical reality is a quiet illusion, not false, not wrong, just incomplete, a useful shadow of a deeper wave-like truth. And this shadow is what allows you to live, to move, to speak, to rest. Because a world completely governed by coherent quantum rules would be chaotic to us, too sensitive, too fragile, too ambiguous. Decoherence is the gentle bridge from the strange to the stable, from the microscopic to the familiar, from the realm of possibility to the realm of experience. And so your world, the world of everyday objects, is born from this blending, quantum at its foundation, classical in its surface behavior, a harmony between uncertainty and definition, between flickering possibility and settled form, between the invisible fluctuations beneath existence and the quiet solidity you rely on each day. The classical world emerges from this smoothing, this gentle erasing of quantum interference, this constant blending of every delicate superposition into a single stable outcome. But decoherence does something more subtle, more profound, than simply choosing a result. It creates a shared frame of reality, a world where different observers agree on what happened, agree on what exists, agree on the structure of their surroundings. This agreement is not built from certainty, but from consistency, a consistency generated by the environment itself. The environment records information, not deliberately, not consciously, but automatically. A photon bounces off a surface and carries with it a tiny imprint of that surface. A molecule vibrates, and its oscillation encodes a trace of what it collided with. A grain of dust absorbs a bit of energy, and its internal state shifts in a way that reflects the moment. The world is constantly copying information into countless channels, broadcasting the classical state of macroscopic objects into its surroundings. This is why if you step into a room, the objects inside do not have to snap into existence. They were already settled, already definite, because the environment had been recording their properties every moment. Millions of photons carrying tiny impressions, thermal vibrations encoding subtle histories, air currents shaping the positions of particles. The environment is a measurement device, far more pervasive than any instrument built by humans. Quantum possibilities do not survive this relentless recording. Superpositions can only persist when they are isolated, shielded, protected from the world, and such protection is extraordinarily rare. An electron in a quiet trap, a superconducting qubit chilled near absolute zero, a carefully prepared photon moving through a controlled channel. These systems can behave quantum mechanically in ways a chair never could, because they are separated from the noisy environment that destroys coherence. But the moment they are exposed, the moment they interact with the uncontrolled real world, their superpositions fade, their quantum patterns dissolve, they become classical, stable, predictable, not because quantum rules have stopped acting, but because decoherence has masked them under layers of environmental memory. And this raises a subtle insight. The classical world is not a separate realm. It is a perspective, a limit, a way the universe appears when quantum information is inaccessible, when the delicate phases have been spread too thinly to retrieve. Classicality is the shadow left behind after the quantum structure has dispersed, a simplified version of a deeper truth, a version that allows matter to hold shape, allows planets to orbit, allows biology to unfold, Without decoherence, atoms would not form molecules, molecules would not form cells, cells would not form organisms, and organisms would not form minds. Life itself requires a stable macroscopic world, a world where objects have identity, where outcomes persist, where causes lead to effects. Decoherence is what gives the universe this continuity. It is the quiet boundary between potential and presence, between the quantum foundations and the lived experience that emerges from them. This boundary is not sharp, not abrupt, but gradual, a smooth transition from coherence to chaos, from possibility to definiteness. Imagine a drop of ink falling into water. At first it is concentrated, structured, recognizable. Then it spreads, diffusing outward, blending into the fluid, its pattern dissolving until no trace remains. Quantum coherence is that drop, decoherence is the diffusion, and classical reality is the uniform water left behind, a calm surface, revealing nothing of the patterns that once existed, even though those patterns were essential for the surface to exist at all. This is the quiet paradox of classical emergence. We live within a stabilized world, yet this stability is born from instability. We rely on definite outcomes, yet those outcomes are carved from a space of countless possibilities. We trust the solidity of objects, yet that solidity is the blurred echo of an underlying wave-like realm. And as physics pushes deeper, as experiments grow ever more precise, we begin to see that the classical world is less fundamental than we once believed, that solidity hides subtlety, that certainty hides probability, that existence hides interference, and that behind every object we touch, every surface we see, every event we witness, there lies a quantum foundation we can never fully observe, only infer, only glimpse through careful experiments and gentle thought. Decoherence is the quiet painter of the macroscopic world, brushing away the fragile strokes of quantum possibility, leaving behind the smooth, coherent image we call reality. And in this understanding comes a deep calm, because the world does not need certainty to be stable. It does not need determinism to be meaningful. It does not need full clarity to support life. It only needs the gentle fading of superpositions, the quiet diffusion of quantum information, the constant conversation between system and environment. A conversation that shapes everything you know, every memory, every action, every sensation, every breath, all resting on the invisible dance between coherence and its dissolution. The world feels solid because superposition cannot survive the flood of interactions that define macroscopic existence. And so you live in the settled surface of a deeper ocean, a surface calm enough to walk upon, but beneath which the currents never stop flowing. And so the world you move through, this world of solid shapes and predictable patterns, is the quiet surface of a deeper quantum ocean, an ocean that never stops shifting, never stops vibrating, never stops exploring possibilities. But at your scale, and at the scale of every familiar object, that ocean is hidden beneath a gentle, constant fog, a fog made of interactions, a fog made of environmental memory, a fog made of decoherence. In this fog, quantum phases cannot survive. Interference cannot form, superpositions cannot stay whole. They spread, they blur, they dissolve, until what remains is a single, stable state, settled enough to build biology, settled enough to build minds, settled enough to build everything you experience as the world. This dissolving does not mean the quantum structure disappears. It only becomes inaccessible, hidden, smeared across too many degrees of freedom to ever gather again. Imagine a delicate melody played softly inside a storm. The melody exists, but the wind tears it apart, scatters the notes into turbulence, and no listener can ever reconstruct its original shape. Decoherence is that storm. The world is filled with its noise, and quantum patterns are the fragile melodies lost within it. Yet without this storm, without this constant scattering, the universe would be unrecognizable. Atoms would behave like waves without boundaries. Macroscopic objects would not retain identity. Your body would not hold shape. Life would be impossible. Conscious experience would have no foundation. Even the flow of time, the feeling that moments follow moments in a sequence, relies on decoherence to preserve a record of what has happened. Without decoherence, there would be no memory, no history, no persistence, only shifting waves of possibility, constantly blending, constantly rearranging. And yet, within the quantum foundations beneath this classical world, there remains a strange truth. Decoherence does not select a single outcome in the deepest sense. it only hides the others. It spreads them out across the environment, making them inaccessible, unrecoverable, irretrievable, not destroyed, just diluted, like faint ripples lost in a vast sea. This distinction is subtle and profound. It reminds us that the classical world is not as absolute as it appears. It is emergent, approximate, a practical reality born from the limits of what information we can access, a reality formed by losing information, not gaining it. This is why no measurement can be perfectly reversed, why no observation can be undone, why you cannot unsee what you have seen. The information that once belonged to a quantum system has been scattered, absorbed, mixed into the environment. The past is sealed because decoherence makes it impossible to return to an unmeasured state. The world does not erase tracks, it multiplies them, burying each one under countless layers of interaction. And so, in this gentle understanding, you can see the universe as a tapestry woven from threads of quantum possibility, but smoothed, blurred, softened by decoherence, made coherent, not by clarity, but by forgetting. A universe that becomes stable through the loss of delicate information. This is the quiet heart of classical reality, not a world separate from the quantum, but a world shaped by what the quantum cannot preserve. A world resting on the limit of what can remain coherent, what can remain pure, what can remain untouched by its surroundings. Every surface you see, every object you hold, every step you take, all of it is defined by decoherence, by the vanishing of interference, by the suppression of superpositions. And yet, somewhere beneath it all, the quantum rules continue to whisper. Their patterns still present, their structure still fundamental, even if hidden, even if washed into the background noise of the cosmos. When you look at a simple rock, when you touch a warm cup, when you watch the wind move across leaves, you are seeing the quiet balance between coherence and its loss, a balance that gives the world its solidity, its reliability, its calm. And in this calm there is a deep peace, a sense that the universe does not need certainty to function. It only needs structure. It only needs interactions. It only needs the gentle dissolving of quantum phases. From this dissolving comes the world. From this forgetting comes stability. From this blurring comes form. And from this steady, quiet process comes the reality you know. The emergence of the classical world is not a sudden change. It is a slow exhale, a diffusion, a settling, a transition from fragile quantum whispers to steady macroscopic presence. And as you breathe, letting your attention soften, letting your mind float gently, you are drifting in that same transition, between clarity and blur, between precision and calm, between potential and presence. Decoherence shapes the world, and now it shapes this moment. Letting your awareness loosen, letting the edges of thought dissolve, letting the mind sink quietly into stillness. You rest now in the quiet after the journey, held softly by the strange foundations you have explored. The quantum world has unfolded around you like a dim landscape lit only by possibilities, a place where certainty flickers, where outcomes are never fixed until they must be, and where nature speaks in the gentle language of probability waves. And as you drift here, the familiar world feels slightly translucent, as if everything solid is made of something far more delicate, far more subtle than you once imagined. Reality, when seen closely, is not a rigid machine. It is a conversation between particles and fields, between measurement and memory, between what can be known and what forever escapes knowing. In this quiet, you can feel how much of existence is built from the invisible, not empty, but filled with fluctuations, with virtual exchanges, with ceaseless motion beneath stillness. The vacuum, which seems silent, is actually alive with trembling fields, with momentary particles that appear and vanish, leaving only a whisper of influence. These are the ingredients from which everything rises. The strength of forces, the masses of particles, the shapes of atoms, the stability of matter, all emerge from these hidden interactions, from this restless background, from the deep framework of quantum fields. And the universe you move through each day is the calm surface of this deeper activity, like seeing only the gentle waves on the top of an ocean, never glimpsing the vast currents moving beneath. You walk in a world of outcomes, but it is built from a world of potentials. Potentials that never fully disappear, even when they seem to collapse into something definite. Some part of every moment remains braided into the unseen. The structure of reality is not rigid, not absolute. It is layered, emergent, quietly shifting. Your everyday world is one layer, the quantum world is another, and the border between them is not a wall, but a soft horizon. A horizon made of decoherence, of blurred phases, of interactions that shape what can survive and what cannot. The classical world feels stable because the quantum world is constantly resetting, constantly dissolving, constantly fragmenting into countless traces that hide the underlying complexity. But that complexity never goes away. It is always here, beneath thought, beneath form, beneath every sensation. A quiet engine, an invisible architecture, a shimmering foundation. As you breathe slowly and your mind drifts, you can feel how this foundation supports everything, how even the atoms making up your breath follow quantum rules, leaping between energy levels, tunneling, entangling, dancing through fields. Every inhale is woven from uncertainty. Every heartbeat is shaped by quantum transitions. Every cell is held together by bonds that arise from the mathematics of the small. And yet you feel none of it directly. You experience the world as smooth, continuous, solid, predictable. This is the gift of emergence, a world of calm built atop a world of motion, a world of stability built atop a world of fluctuations, a world of definiteness built atop a world where nothing is truly definite. In this gentle realization there is a deep peace. You do not need to hold the whole universe in your mind. You do not need to grasp its equations, its operators, its Hilbert spaces, its symmetries. It is enough to know that the world is layered, and that beneath every familiar experience lies a quiet complexity that does not demand understanding. It simply exists, softly, silently, faithfully, supporting reality. Quantum physics is not a requirement for living. It is a window into the hidden machinery of existence, a window into the strangeness that makes normal life possible, a window into the subtlety behind every ordinary moment. And when you look through this window, as you are doing now, you see not chaos, not confusion, but an elegant structure, a structure built from rules that are strange yet precise, rules that appear mysterious yet never violated, rules that feel dreamlike yet govern everything with perfect consistency. In the softness of this moment, you can sense a gentle balance, the balance between potential and actuality, between openness and closure, between what can be known and what remains forever hidden. The quantum world is not random. It is patterned, it is mathematical, it is coherent in its own quiet way, and those patterns are the reason the larger world can exist, the reason matter holds together, the reason forces behave as they do, the reason reality has architecture. In the quiet of this space, you can feel those patterns beneath everything, not sharply, not clearly, but as a soft presence, a subtle hum, a tremble beneath the surface, like the lowest note in a vast cosmic chord, a note that supports the whole harmony, yet rarely reaches awareness. This hum is the language beneath reality, a language of probabilities, of amplitudes, of shifting phases, and even without understanding its full grammar, you can feel its calmness, its order, its steadiness. It is the quiet beneath existence, the stillness beneath the complexity, and as your thoughts drift slower and softer, you become a part of that calm, a part of the same quantum fabric, a part of the same field-filled world, a part of the same unfolding. Nothing separates you from the physics you have been exploring. You are made of the same particles, the same fields, the same probabilities. You are a structure arising from the same rules, a ripple within the same fabric, a temporary form within the same endless unfolding. In this realization there is comfort, there is belonging, there is peace, and slowly, gently, the world grows soft, thought grows quiet, and the boundaries between things feel less rigid, less necessary, less defined. There is only the slow exhale of the universe, and you settling deeper into the quiet, into the subtle language beneath all reality. And now, the patterns you have followed through this long, quiet journey begin to blur into something softer, something that feels less like knowledge and more like a feeling of how delicate reality is beneath the surface, a feeling of how every stable experience rests on rules that are anything but stable, a feeling that certainty, the kind you use to move through your day, is built on top of probability, and that probability is not just a mathematical idea, but the deep architecture of existence. When you look inward now, you can almost sense how the world is held together by this invisible scaffolding, not by rigid beams, but by shifting tendencies, by patterns of likelihood, by waves that spread and interfere and collapse into the shapes you call objects. The solidity you know is a kind of illusion, not a deception, just an emergent calm, arising from countless events that never become visible. The quantum world works tirelessly to keep everything stable enough for a larger world to form. Atoms settle into shells because of the strange balance between attraction and quantization. Electrons remain suspended around nuclei not because they orbit like planets, but because their wave functions spread and settle into shapes that minimize energy. They are not circling, they are standing, locked into patterns that emerge from the mathematics of the small. And you, your body, your breath, your thoughts, are built from those standing waves. Your entire being rests upon solutions to equations that never stop vibrating. Even the calm you feel right now is supported by a world that never rests. There is comfort in that, a comfort that comes from knowing the universe does not require your effort to function. It unfolds on its own, quietly, faithfully, with a precision far beyond intention. Every electron in your body follows quantum rules. Never confused, never uncertain in the way people are uncertain, its uncertainty is built into its nature, not a flaw, not a gap, but a defining property, a property that makes your existence possible. Without uncertainty, atoms would collapse, molecules would not bind, stars would not shine. Uncertainty is not limitation, it is structure, it is stability. It is the gentle foundation that holds the universe together. As your awareness drifts, you can feel how strange that is. And how peaceful. The unpredictability that defines the quantum world is the reason you can exist at all. Randomness is not chaos. It is the quiet engine driving creation. Every fluctuation in the vacuum, every jitter of a particle, every shift in a field's amplitude, these tiny motions are what allow energy to be exchanged, reactions to occur, forces to operate. A universe with no quantum fluctuations would be silent, still, cold. A universe with no probabilities would be frozen. Motion comes from uncertainty. Life comes from motion. Thought comes from life. And so your very consciousness rests upon the trembling of fields, upon the constant background hum that fills the vacuum. Even the emptiness is full of hidden activity, full of potential exchanges, full of virtual events that never become real but never stop influencing what is real. You are surrounded by this subtle activity, and made from it. There is no separation between the quantum world and the familiar world. They are not two places, not two realms. They are one continuum, seen at different resolutions. One reality, expressing itself in different ways. When you zoom out, the world becomes classical, stable, solid. When you zoom in, the same world becomes fluid, blurry, probabilistic. There is no boundary, only a gradient, a gentle transition from approximation to precision, from simplicity to complexity. And even now, as your thoughts slow, you are part of this gradient. Your awareness is one layer, your cells another, your atoms another still, and beneath them, your quantum components follow rules that have operated since the beginning, rules that always work, always apply, always guide the unfolding of reality. Whether or not they are understood, they continue. This is why you can let go. The world does not require your control. It does not need your attention to maintain itself. It is self-maintaining, self-evolving, self-consistent. Even when you sleep, even when you drift, even when you sink into the deepest quiet, the universe carries on. The fields continue to ripple. The atoms continue to resonate. The probabilities continue to flow. Reality continues to unfold, and you are carried by it, not separate from it, not outside it, but inside it, woven into it. A pattern within the larger pattern, a moment within the larger flow. The quiet beneath your mind mirrors the quiet beneath reality. Both are made of stillness resting upon motion. Both are formed from layers of activity that fall away as attention softens. The deeper you drift, the more the complexity fades, and the more only the softness remains. A softness that has always been there, waiting beneath the noise, waiting beneath the definitions, beneath the boundaries, beneath the questions. You do not need to solve anything, not tonight, not now. The quantum world does not ask for answers. It simply offers a glimpse of how strange and beautiful reality truly is, a glimpse that you can carry without needing completeness. Understanding is not a requirement for peace, and so you settle deeper into the gentle hum beneath existence. the hum that supports every structure, every form, every moment, the quiet beneath all things. And so, as you drift deeper into this quiet reflection, a sense of softness begins to settle over everything. You can feel how the small supports the large, how the invisible supports the visible, how the uncertain supports everything that feels certain to you. The quantum world is not a different place, not a hidden basement layer beneath the universe. It is the universe in its most fundamental form, a world where probabilities flow like gentle currents, where particles are not truly particles but temporary shapes taken by deeper fields, where motion is not a path but a change in distribution, where existence itself is not a fixed state but a continuous process, a process that unfolds in quiet waves, waves that never stop carrying information, momentum, energy, waves that interfere, combine, separate, and collapse. Each event a moment of resolution, each collapse a small decision the universe makes. A decision not driven by intention, but by the mathematics of quantum structure. Every time a photon interacts, every time an electron binds, every time a nucleus emits a particle, the quantum world asserts itself, softly, quietly, impossibly fast, and impossibly small. It is not a world you can see, but it is a world you exist within. Every thought you have requires electrons jumping between energy levels, releasing tiny packets of light, moving through synapses with quantum precision. Every breath you take depends on bonds formed by wave functions overlapping in just the right shapes. Every heartbeat depends on quantum tunneling within the reactions that allow potassium and calcium to move across membranes. The machinery of life is quantum machinery. Your existence is quantum existence. And yet you live in the classical world, a world where you do not see superpositions, you do not notice probabilities, you do not feel the constant fluctuations beneath you. This is the gift of decoherence, the quiet process that hides the quantum rules to allow stability. Without it, the world would shimmer with possibilities, never settling, never taking shape. You see the tree, not the countless quantum histories that could have formed it. You see a chair, not the overlapping superpositions that cancel each other out. You see your own hands, not the probability clouds that define the positions of their atoms. The classical world is not more real. It is simply a filtered version of the quantum world, a version tamed by interaction, smoothed by environment, stabilized by the constant exchange of information. The universe is continuously measuring itself, not through conscious observers, but through contact, through scattering, through entanglement. Every collision is a kind of measurement. Every exchange is a spreading of information, and as information spreads, superpositions fade, leaving a single configuration, not because the universe chooses, but because the environment forces consistency. A photon reflecting off a leaf collapses its position. A molecule bumping into another collapses its state. A warm object constantly exchanging energy collapses the possibilities of every particle inside it. This quiet, constant collapse is the reason you experience a world with solid shapes, with stable objects, with predictable behaviors. Decoherence is the bridge between the strange rules of the small and the familiar rules of the large, a bridge that you cross every moment, without noticing. And yet, even with this bridge, the quantum world never disappears. It continues to operate beneath every perception. Particles tunnel through barriers inside your cells. Electrons spread into probability waves inside every atom. Fields ripple in empty space, even when nothing seems to happen. Every object you see has quantum roots. Every sensation you feel arises from quantum transitions. Every moment of calm rests on vibrations too small to witness, but too important to ignore. When you breathe slowly now, you can imagine those tiny fluctuations, subtle waves in the vacuum, the gentle trembling of fields, the quiet shimmer beneath existence. Not chaotic, not violent, just soft, a background stillness with texture, a calm with motion inside it, like a lake so still that only small ripples hint at its depth. The universe is not silent, but its noise is softer than silence, a noise made of probabilities, waves, and interactions. And as you drift, you become aware of how peaceful that foundation truly is. The quantum world is not trying to confuse you. It is simply operating on a scale where the usual concepts cannot apply. Certainty breaks down. Position becomes a cloud. Motion becomes a distribution. Connection becomes non-local. Barriers become permeable. Empty space becomes full. Every rule rearranges itself. not to be strange, but to be accurate. And yet in this strangeness there is harmony. A harmony that supports galaxies, atoms, life, thought, and rest. A harmony that continues whether or not you pay attention, whether or not you are awake, whether or not you are aware. Even now, as your mind quiets, the quantum world continues its gentle work. No effort needed, no awareness required. Everything happens by the nature of what is. And the deeper you drift, the more natural that feels. You can let go because nothing in the universe depends on you holding on. You are carried by laws that have held the cosmos from the beginning. You are supported by structures far older than stars. You are grounded by patterns that never break. Even when they appear strange, they remain consistent. Even when they appear uncertain, they remain precise. Even when they appear paradoxical, they remain coherent. Reality does not ask for understanding. It simply continues, and so do you. You drift with the quiet fabric beneath everything, floating on a foundation of gentle probabilities, resting on the strange yet peaceful rules of the small. And so, as the quiet of the quantum world settles around you, the final threads of this long, gentle journey begin to weave themselves together. Not into certainty, not into a final answer, but into a soft understanding. A calm acceptance that reality is deeper and more intricate than the surface ever reveals. You have drifted through waves of possibility, through the strange symmetry of particles that behave like both matter and motion. You have wandered through slits in space, where particles create patterns by interfering with themselves, as though each one carries a private map of all the paths it could take. You have visited the boundary of knowledge, where uncertainty is not a lack of information, but a fundamental description of what the universe allows. You have traveled across invisible threads, where entangled particles share states in ways that ignore distance. A silent choreography connecting one place to another. You have slipped through barriers, watching particles appear on the far side of places they should not reach, not by breaking rules, but by obeying rules that are simply not intuitive to us. You have floated within fields, the deepest level of physical reality we know, where particles are nothing more than excitations, brief ripples in continuous oceans that fill all of space. You have crossed the border between quantum strangeness and classical clarity, a border sharpened by decoherence, the quiet dissolving of superpositions into definite outcomes. Now, all of these ideas gather around you, not demanding understanding, not insisting on attention, but resting gently like a soft glow beneath the surface of thought. The quantum world is a world that challenges intuition, because intuition is built from experiences in a macroscopic realm. A realm where objects follow predictable paths, where events have clear causes, where possibilities collapse into single outcomes so quickly that alternatives are never seen. But beneath that realm, something different moves, something quieter, more fluid, more probabilistic, yet no less real. Reality at the smallest scales is not a collection of things. It is a set of rules, a pattern of behavior, a mathematical rhythm, a rhythm that unfolds everywhere, in every moment, in every atom, and even now as you drift deeper, you remain supported by those rules. You are not separate from them, you are woven directly into them. Every atom in your body is guided by probability waves, by the spread of possible positions, by the constraints of uncertainty. Yet together in aggregate they form something stable, something whole, a person with thoughts, with sensations, with presence. The macroscopic world emerges from the quantum world, not by replacing it, but by averaging it, smoothing it, taming it through interaction. And so you walk every day through a universe built from fluctuations you never see. A universe that looks solid but is rooted in continuous motion. A universe that behaves predictably because countless interactions erase superpositions before they reach your senses. When you touch a surface, you feel stability, but beneath that stability, electrons repel each other through quantized forces. When you see light, you see clarity, but beneath that clarity, photons are absorbed and emitted as discrete packets. When you listen, your ears respond to vibrations, but beneath those vibrations are the quantum transitions that define energy levels. The classical world is quantum behavior scaled upward, washed clean of ambiguity, made smooth by numbers. The same rules apply, only their texture changes. At the smallest scales, probabilities dominate. At the largest, patterns dominate. Between them is you, a being made of particles whose positions can never be perfectly known, a being whose atoms are constantly exchanging energy, constantly interacting, constantly decohering, so that your world remains recognizable. A being who carries within every cell the signature of quantum mechanics, yet experiences life through the familiar clarity of macroscopic existence. There is beauty in that duality. The universe does not need to choose one form. It can be both, wave and particle, probability and outcome, possibility and reality, quantum and classical. You can breathe into that duality now, letting the complexity soften into simplicity, letting the questions fade into calm, letting the strangeness become gentle. Because the quantum world does not ask you to understand every detail. It simply invites you to notice that beneath everything familiar there are deeper patterns, quieter motions, subtle rhythms, a hidden language written in mathematics, but felt as existence. A language that underlies the stability of matter, the structure of atoms, the warmth of stars, the chemistry of life, and the stillness you feel now. Resting in this awareness does not require effort. There is nothing to solve, nothing to memorize, nothing to grasp, only the sense that reality is layered, and that each layer is more remarkable than the one above it. You are drifting now toward a place where the boundary between thought and quiet grows thin, where the rhythm of your breath slows into alignment with the slow vibrations of the world beneath, where the strangeness of quantum rules becomes comforting. Because the universe does not need simplicity to be peaceful, it does not need certainty to be reassuring, it does not need clarity to offer rest. Even in its most fundamental form, even in its least intuitive behaviors, the universe remains a place of order, a place where laws hold, where patterns endure, where everything works together in harmony, and that harmony is carrying you now, gently, steadily, softly. You can let go into that harmony, resting in the knowledge that every moment, every sensation, every breath is supported by the same quiet rules that shape galaxies, stars, atoms, and space itself. There is a language beneath reality, a language you do not hear but you feel, a language of probability, of connection, of waves that guide existence, and fields that hold the universe in their invisible arms. And as you drift deeper into rest, that language continues speaking, quietly, faithfully, without interruption, carrying you into calm, into stillness, into the gentle mystery that lies beneath all things.